Okay, today we're going to talk about a couple things. We're going to start with why measure airflow rates. Okay, you can't manage what you don't measure, right? And the major reason for me when it comes to a lot of our facilities is simply provide acceptable indoor air quality. I think it's very important that you measure airflow rates, and particularly outdoor air, but maybe equivalent clean air. It's also important for building pressurization, which is very important for air quality. Also, those of you that are engineers or even owners, reduce your IQ liability. There's we're going to get into reasons how, why, and how you should limit your IQ liability. And then, of course, everybody's very interested in saving energy. And if we're not controlling things, we're really not going to be saving energy. And then that kind of runs into improved building performance. Improved building performance, in my mind, is going to be a combination of control and monitoring. Today we're going to probably talk more about control than monitoring. And then finally, I called it pandemic mode for a long time, but infectious risk management mode. If we get back into something like COVID again, we're going to have to really pay attention. I don't think we did a very good job of preparing ourselves for if this were to happen again with our systems. Once we talk about why measure airflow rates, the next thing we're going to want to do is we're going to talk about why choose EBTRON. I think that's going to be easier, actually. But at any rate, we're going to talk about that at the end of this presentation. All right? So let's go back to why measure airflow rates. Well, one of the benefits of providing acceptable indoor air quality is going to be simply outdoor air. I mean, outdoor air, like it or not, is essential to dilute indoor contaminants. I don't think we're ever going to get to the point where we do it all by filtration alone, and so it's a combination of basically filtration and outdoor air, and really our standards, our codes are really based on ventilation rates. There's a push towards equivalent clean air using high level filtration, and that's okay too. But don't forget that. If you're making a claim on equivalent clean air, you need to know how much equivalent clean air you're providing. And then building pressure and IQ, it's really limiting the transport of untreated outdoor air and moisture into a building. When you're east of the Rockies, it's pretty simple to understand the moisture side of it. Maybe the Pacific Southwest, it's a big deal if we run a building negative. But it's not just moisture, it's untreated outdoor air in general. And we're going to find that the best way to do that is by controlling the pressurization flow, and that's going to be based on measuring airflow rates. So that's our first benefit. Our second benefit is going to be reduce your IQ liability. Our building codes specify minimum outdoor air ventilation rates, period. It doesn't matter where you are. It doesn't matter if you're running the IMC, the UMC. It doesn't matter if you're in California. It doesn't matter if you have a modified code. They're all based on airflow rates. They're all pretty much driven by ASHRAE standards, with the exception of California, really. They're driven by ASHRAE standards. And then, of course, there's this pressurization requirement. And we're going to talk about, how do you limit your IQ liability? It may not be as straightforward as some people will come and say to me, well, yes, I'm going to measure outdoor airflow rates, for instance, to show code compliance. It's like, well, you can show code compliance with test and balance. It's going to be a little deeper than that, okay? It's going to be an operational thing. On the save energy side, I'm going to spend most of my time talking about outdoor air. Why? Outdoor air is the most expensive thing in our HVAC system to condition. It's a big energy hog. I get it. People would like to, minimize it. But the bottom line is we're going to have to control it. We're going to have to look at what affects outdoor airflow rates. And we're going to get into that. And we're also going to talk about when you do demand controlled ventilation and why airflow measurement, particularly outside airflow measurement, should be incorporated into your DCV strategies. Okay? Improved building performance, is kind of like a catch-all. When we go through all these different we go through all these different things that we're going to talk about in this presentation, we can't provide acceptable IQ or maintain building pressure if we're not really measuring and controlling. And those things really affect temperature and humidity control and energy. And then really on the monitoring side, something I'm not going to get into a whole lot today is detect system problems. Facility people simply don't have enough help. And it's really difficult. Normally, folks don't deal with a problem until somebody reports it as a problem, and it's often too late then. Infectious risk management mode, pandemic mode. It's to me, it's a little bit unfortunate that we seem to have forgotten all about COVID. It isn't that long ago. We didn't really do enough to improve our building systems, HVAC systems. So we're going to talk about things that we could do. And how do you toggle back between normal and IRMM mode? I think that'll be pretty important, okay? All right, that's just a quick summary of the things that we're going to talk about, and I will come back and go into different areas in more detail. All right, so stay tuned. Thanks. Okay, in this presentation, it's relatively short. We're going to talk about indoor air quality fundamentals, a little bit about dilution and contaminant removal, and also pressurization in terms of limiting the infiltration of untreated outdoor air. Okay, so, to keep it simple, I've always done these presentations this way. I like to just keep it simple for mechanical folks and just say, look, let's understand the contaminants of concern. We might have building generated, could share, VOCs, but it could be other chemicals. We have biological. Typically, biological have always been a result of moisture. So within the building envelope or an intake plenum, supplier plenums, these are things that are either pressurization driven or airflow rate driven. Outdoor generated, we just have to remember that the outdoor air itself could be a problem. We've gone into, when I say via the HVAC system, I've gone into many systems over my career where, filters they're either not maintained, they're not even in place in some cases. That's kind of at the air handler. But through doors across the building envelope, again, those are created by pressurization problems, negative pressure problems. And of course, we're in occupied spaces, so occupant generated typically has been body odor. Now, 2020 kind of changed that a bit, and now we have to start to consider airborne pathogens. COVID really did change things, and so we have to also consider that, where typically we were only dealing with this in healthcare facilities. All right, now, again, trying to keep it simple, basically here we have an occupied space, that's that box, and there's some degree of contaminants, in that space. But if we don't have any outdoor air for dilution, or we don't have any targeted high-level filtration, meaning filtration that we know is going to remove the contaminant of concern, what will happen is the contaminant rate will just build up. And going back to COVID, that's kind of exactly what happened. People that went home sick got everybody else sick because, let's face it, residences have probably the worst HVAC system. They have very little outdoor air, and they have really very poor filtration. Okay, so but it could be any contaminant of concern. All right, so what do we do? Okay, well, there's the fundamentals, and I really kind of go crazy about this a little bit because it's like during COVID, I saw everybody do everything but the fundamentals. Okay, it's like, listen, it's okay to do things that might enhance filter. How well filters work. It might be okay to use UV light to kill things, but to be honest with you, if you don't do the fundamentals, you're going to have a problem, okay? It's just like, I'm a big sports fan, love football. You're never going to find a football team that's any good that isn't fundamentally sound, okay? Well, you're never going to find a healthy building that isn't fundamentally sound, okay? So what are the two things that we need fundamentally? We do it in healthcare all the time. We have outdoor air for dilution. I said replace here just because I like to do these R things, replace, remove, get people remembering things. And we remove through filtration, okay? And basically, what we do in healthcare is outdoor air changes have to do with dilution, and room air changes have to do with filtration, okay? And so you have to do both of these, and if you do both of these properly, you're going to maintain your contaminants at a level below a threshold where they're not going to be of concern, all right? Now, the problem here is we're not going to talk about air cleaning. I mean, that's not what we do, okay? We're going to talk about airflow measurement and control. That is what we do. So, when you take a look at this, you just cannot set it and forget it. And that's what a lot of our systems do. And I show a recirculating air handling unit here. It's not just recirculating air handling units. It's dedicated outdoor air systems. It's all of our systems. We set it, we forget it. We don't necessarily maintain it. We don't know if things go wrong. And so, I'm going to show you in a subsequent presentation that you just can't set it and forget it. And it's going to be because of fan speed changes and systems that have fans that change speeds. But it's also going to be wind and stack pressure on all systems, okay? Basically, that's something that seems to always get overlooked. And that if we have dampers, well, you know what? We have damper issues too. And I'm going to show you that these errors are, if you just set it and forget it, if you're within 50% of your set point, you're having a good day, and it's probably considerably worse than that, okay? But, at this point, I just want to mention it to you, get you thinking about what we're going to talk about, all right? When it comes down to building pressure and indoor air quality, building pressure is another thing that's often overlooked. So when you look at that map on the left, the map on the left was a result of work. I was working on things in the early 90s with EBTRON, and I was going out to non-healthcare or laboratory facilities and saying, hey, you should be concerned with building pressure, and I would basically get laughed out of the offices that I would go see. They're like, we don't really care as long as we can get doors open. And I was like, well, that's not true. I said, we have to really concern ourselves with untreated outdoor air coming into the building, and particularly moisture. Okay, so, I was kind of lucky. My buddy was my roommate in college, still a good friend of mine. He was a professor of meteorology at Penn State. He had his own weather business. I remember in the early 90s, you just didn't go look things up on the internet. And I said to him, hey, can I get some data on, weather data? And he gave me 700 weather stations of wet bulb, dry bulb data over a 10-year period. And I took some of that data and I said, well, I need to know where the moisture is a problem. And because that's where I want to really focus. Untreated outdoor air is a big deal. There's dirt, there's dust, there's all kinds of things in the outdoor air. But when you have a lot of moisture, it's really a bigger problem. And so I created that map on the left. I just looked at larger cities. There's microclimates that I'm leaving out. But basically, east of the Rockies, you have a problem. It doesn't even matter. And I always laugh at my friends in Canada. I go, hey, I know that this goes up into Canada. I just didn't do it that way back then. Okay, and then you have the Pacific Southwest who has some moisture that you have to concern yourself with. So when you look at that, negative building brings in a lot of moisture. It also brings in untreated outdoor air, dirt, dust, pollen, whatever's out there. It causes perimeter temperature control problems. And so it's something that we want to avoid. So the other thing that I did with that data was I said, well, how much moisture is actually transported? Because there's basically, to me, there's three transport paths that I'm concerned with. One is just basically leaks. Leaks are a big transport path of water into a building. But there's vapor pressure gradients, and but there's also pressure-driven water transport. And so when I looked at that data, I found, obviously if you were in Florida or you were in Hawaii, you had a tremendous amount of moisture. I mean, all I'm doing here is I'm looking at running a building 1,000 CFM negative when the dew point is over 65 degrees. I picked 65 degrees back then because 65 degrees ended up with an envelope moisture potential of about 70% RH, okay, which was at the time, in my, based on everything I looked at, was, a number where above that you really have to really concern yourself with mold and fungal growth. It's not that below it you don't have to, it's that it just really is a bigger problem above it. I think if I did it today, I would have done it probably at 60, but you know what? I'm not going to do it again because this gets my point across. But if you look at there on the left, Miami, Honolulu, Miami, almost 1,000 gallons of water is transported per 1,000 CFM negative, okay? And that's running 24/7 during those periods. But, I go into these buildings down in Florida where they turn off the outdoor air during unoccupied periods, but they still have facility people in the building, and they're still running toilet exhausts, and, so there's a problem there, okay? And then the condensing moisture was the darker orange, almost red color, I guess, which shows, basically just go ahead and dump some water on the walls. All right, well, I did that for a while, and then I looked at it, and I realized that it wasn't really how much moisture did you transport a year, it was how much moisture did you transport a day, because it doesn't take that long for these molds to start growing and develop and really become a problem. So it doesn't matter where you are, okay? If the dew point's over 60 or 65 degrees, you're running a building negative, you have a potential problem, okay? And that's really what we're trying to do there. Okay, this is a very short presentation. Again, it's my introduction to indoor air quality, but it kind of covers the problems, all right? So we're gonna come back now next, and we're gonna get even a little bit deeper into our discussion, okay? Next. Okay, now we're going to take a look at standard and code requirements, but we're not really going to go into a lot of detail about these standards or these codes. We don't really have enough time to do that, but we are going to talk about outdoor air and building pressure, okay? And so let's just start with something that I think is the easiest way to look at standards and codes from my perspective and the use of airflow measurement. It's real simple. All codes specify outdoor air flow rates, okay? They just do, all right? It doesn't matter if it's the IMC, the UMC, even in California, California's mechanical code they're based on standard 62, but they're airflow rate based standards. Then you have, of course, also in California, for those of you from California, we have the California Energy Code, which is Title 24, Part 6, and it's still a rate-based standard. The difference, the real driving difference, is the ventilation rates required. So, to me, it doesn't matter. And then you have states that have their own codes, but they're just variants of one of these two codes, okay? So, to me, the thing is, I've always thought about this as, I've listened to a lot of reps sell our product to engineers on code compliance, and that's fine. But you have to remember, from the way I see it, is that code compliance is an instant in time, okay? And if test and balance goes in and make sure that you've provided the code required ventilation that you've put on your plans, you've satisfied code. That to me is, yes, I can do that by putting our products in, but I don't think that that's the primary reason to do it, okay? I think the bigger deal is that these buildings change, or they may change after occupancy, or they may not change after occupancy, okay? So what you want to be able to do is, we're going to see that if you don't control it, the flow rates, particularly on outdoor air, vary quite a bit. But even so, it's good to use the flow measurement devices to not just control, but to monitor and log, so that if somebody comes in after the fact and changes the way that building operates, okay, and then, down the road that building gets into some kind of litigation for air quality, which I think is coming, I saw it happen in the 90s, and a lot. There was a lot of litigation in the 90s from air quality problems in the 80s, and I think it's just a matter of time before this happens again, because it's pretty easy to go into a lot of these buildings and show that they're not providing proper ventilation, and I just think it's a matter of time before attorneys figure this out. Okay, but anyhow, to me, the thing to do, it's yes, you're going to put this equipment in, you're going to monitor, you're going to control, you're going to log, and it's going to, if somebody changes the system, you have evidence that the system changed. On the other hand, if somebody didn't change the system and you design that system to code, you have evidence that you've provided the code level ventilation. I think these are all really important things. Okay. Now, without going into a lot of detail here, I'll go into a little bit. Okay. So when we look at standard 62, all right, in systems and equipment, it comes a little bit short of talking about permanently measuring and controlling. Unfortunately, it does and it doesn't. I mean, you kind of have to read between the lines here. I mean, it says designing for air balancing. Ventilation air distribution systems shall be provided that allow field verification of outdoor air intake flow rates during operation. Okay, that's interesting, field verification. But then it goes on to say here, designing for varying loads and operating conditions, the ventilation air distribution system for VAV and multi-speed constant volume applications shall be provided with means to adjust the system to achieve at least the ventilation rate, the minimum ventilation airflow as required by Section 6, I'm sorry. And Section 6 is not just the ventilation rate procedure. It could have been the indoor air quality procedure, depending on where you're operating. Under any load condition or dynamic reset condition, I mean, you're only going to pull that off if you're doing active control. And you're really only going to pull that off if you're measuring outside airflow rates. Okay? That's the only way that I think it's going to work out. We keep going with systems and equipment. And again, this applies to all procedures. There at 5.18.1, all systems shall be provided with manual or automatic controls to maintain not less than the outdoor air intake flow required by Section 6 under all load conditions or dynamic reset conditions. Again, that's only going to happen if you're measuring it. And then systems with fan supplying variable primary air. And that can be an air handler, but that can also be a fan coil. Okay, shall be provided with any combination of control equipment, methods, or devices to maintain no less than the outdoor air intake flow required for compliance with Section 5.18.1 above. Okay? Now, I only put the IMC in here, okay, because, again, it's just a matter of time. The IMC is really based on the ventilation rate procedure, Standard 62. And so when you look at Standard 62, the ventilation rate procedure, it's a prescriptive design procedure, presented in Section 6.2, in which outdoor air intake rates are determined based on space type application, occupancy level, and floor area. Okay. That's basically how it is. That's how you calculate the amount of outdoor air that you need to provide. Unless you're going for a provision for DCV, and then it's kind of a variable outdoor airflow rate based on a varying occupancy level, which we're going to talk about too. When you look at the IMC, and you can just look this up if you don't believe me, but really the IMC is a strict interpretation of the ventilation rate procedure. I mean, it's just basically, it almost looks like the ventilation rate procedure. Okay, now, I put this in because there is the alternate procedure that a lot of you use, and you use this to reduce the outdoor airflow rate, okay? That's not necessarily why the IAQP was started, but it's where the IAQP is today, okay? So, again, the IAQ procedure is an alternate ventilation procedure that shall determine the necessary rate of outdoor airflow. You still need to know what the airflow rate is. It's just a different way of determining the airflow rate, okay? And it's all about based on your your contaminants of concern in the space. Now, the thing that I find interesting that a lot of folks kind of overlook that happened, in recent history and Standard 62, is that last sentence on the left there that says verification of occupant satisfaction and indoor DC concentrations shall be performed after the building is completed. And there's a whole procedure for testing the building. And I do think that that could be a problem for a lot of these buildings where you've made a claim to reduce the outdoor air based on air cleaning, okay? Because when you go over to the IMC and you look at the IMC, there is a provision for you to do this, okay? It says, in that same section that talks about the ventilation rate procedure, it says exception, where the registered design professional demonstrates that an engineered ventilation system design will prevent the maximum concentration of contaminants from exceeding that obtainable by the rate of outdoor air ventilation determined in accordance with section 403.3, which is the ventilation rate procedure. The minimum required rate of outdoor air shall be reduced in accordance with such engineered system design. I want you to keep in mind, you can do that if you want to do it. It doesn't matter to me what you do, because your requirements for flow measurement actually is greater on the IQP because your margin of error is less, okay? But as an engineer, you're assuming all risk, okay? And you just need to understand that, right? If you downsize a system and down the road there's a problem, somebody comes in and finds out that, hey, you know what, there is an air quality problem here, you can't go back and say, well, I did this to code level ventilation. You didn't. You made your decision on what you were going to do. And you most likely can't increase that outdoor air. So just think about that part of it. Again, it doesn't matter to me what you do, but I don't feel like enough people are telling you that. Okay? Things, we can go into a lot of different documents that talk about airflow measurement requirements. I picked the IGCC just because it is a code type document, okay? And, basically when you look at the IGCC, it says, hey, each mechanical ventilation system shall be configured to allow for the measurement of outdoor air intake for the use in testing and balancing, recommissioning, and outdoor air monitoring as required by section 801.3.1.2.2, okay, which is bullet, and which says monitoring requirements. Each mechanical ventilation system shall have a permanently installed device to measure the minimum outdoor air flow. There are some exceptions, but that's something that I want you to think about, okay? Those of you we have on from California, basically California Title 24 Part 6, in my opinion, the biggest difference is just how you calculate the ventilation rate. We could go through all of this Title 24 Part 6 stuff and compliance, but the bottom line is the rates are different than Standard 62, and they're based on typically 15 CFM per person, which is associated with diluting body odor. It's the one thing I actually do like. I think that's when you look at Standard 62, I think you find that for some spaces, the outdoor air required is just simply too low, okay? I like the Title 24 is 15 cubic feet per minute with a lower limit based on the space type. Some people have a hard time believing I'm saying this, but I sure would be happy to see Standard 62 move in this direction. I don't necessarily agree with how Title 24 Part 6 handles multi-zone recirculating systems, but you know what? That's for another day. But I do think the ventilation rates make some sense. Okay. The other thing I said I would talk about and briefly talk about is the control of pressurization flow. We're going to talk more about pressurization. Again, we're trying to put a lot of things in a short period of time. But both ASHRAE in California, ASHRAE 62.1 in California, Title 24, Part 6, basically talk about controlling the pressurization flow. I mean, they may not call it the pressurization flow, but that's really what it is, that the mechanical ins need to exceed the mechanical outs to maintain proper building pressure, right? Okay, so again, that's another short presentation, but it's going to help move us into, deeper in the way that this series works. Every presentation gets a little bit deeper. All right, so I'll be back to get a little bit deeper. Okay, in our deeper dive, we're going to talk about factors that affect outdoor air delivery in this case, we're going to talk about recirculating fan systems, although quite honestly, you can apply some of this to DOAS systems. It's just recirculating air systems have even more problems, really. So we're going to look at fan speed changes, wind and stack pressure, and damper issues, okay? So in a previous presentation, we had this slide that talked about fan speed changes, wind and stack pressure, damper issues. And if you just set and forget your outdoor air, meaning you went out with test and balance, you set it up, you walked away, you'd end up finding that if you continuously monitored the outdoor airflow rates, you'd find that they varied at least 50% of the desired set point, and most likely considerably more than that, actually. That's a problem when you're in minimum outdoor air mode, on systems that have an air side economizer or on systems that don't have any economizer at all. Okay, so that's just a big problem. Okay, so that brings us back to a long time ago, which kind of dates me quite a bit. We published this paper in January of 1990 in ASHRAE Journal. I was pretty young at the time. I think I guess I was still in my 20s, 28. And so the person that really spearheaded this whole thing was David Solberg, the primary author there. Dave is still an extremely intelligent person and well ahead of his time. He put together this paper that really helped people understand some of the problems they had or we're going to see. Historically, before 6289, ASHRAE's ventilation rates for acceptable indoor air quality were very low, like 5 CFM per person, unless it was a smoking space. And we had a lot of problems in the 70s and 80s with air quality. We went away from operable windows in the 70s. On a lot of facilities, the ventilation rates were low. We had an energy crisis in the 70s, which drove energy folks to reduce outdoor air. Not that different from what we're seeing today. Okay, so everything was driven to lower the outside airflow rates. And it really created some problems, so that when 89 came around, the ventilation rates got considerably higher, like an office was 20 CFM per person and a classroom was 15 CFM per person. These systems really couldn't handle it properly, okay? And so we wanted to demonstrate that problem, and we did, okay? And the easiest way to look at it is just look at it with a supply fan. I mean, when we did the paper had a supply and return fan in it. It does complicate things, but when you just have a supply fan, it's easier to understand the math. It's not that things are necessarily any different. It's just easier to understand the math. Okay, so basically what we have here, when we have a fixed minimum position intake damper, that lower right, okay, it's a fixed orifice. Okay, so it's got a fixed flow coefficient associated with it. And so that for, say, design supply air, which is what we're showing now, we have a certain amount of outdoor air that's coming in. Well, as we reduce the supply airflow, the mixed air plenum pressure changes and the outdoor airflow changes, as well as does the return airflow. So, there's a lot of things going on here. But from a dilution perspective, you're reducing the outdoor air. It also creates some pressurization problems. But the bottom line is, when you take a look at this, and we made a very specific example. I'm making a very specific example here, that the pressure drop across that intake damper and that louver at design outdoor air at design CFM is 3/10 of an inch. So the mixing box is 3/10 of an inch negative. I do this because I want to be able to show some other things. Okay, so we have basically at design, we have a mixing box that's, negative 3/10 of an inch. Your air handler or system may have a different pressure in the mixing box. Could be less. A lot of your packaged units have less of a pressure drop, and some of your built-up systems have more of a pressure drop. It ends up that the more the pressure drop, the less the problem, but the problem's still going to be there either way. So that as we reduce the supply airflow rate, we follow this kind of square root relationship. So in this case, if we go from 100% supply to 60% supply, we would go from that negative 3/10 of an inch to just a little bit, greater than negative 0.1. Okay, so I'm just going to say it's a 2/10 of an inch change to make it simple. 2/10 of an inch change in pressure. Okay, now if you were to look at the relationship to the outside air, you would find it's a linear relationship. Okay, so that as I drop the supply airflow from 100% to 60%, fixed damper, the outside air is going to drop proportionally with it. It's going to drop from 100 to 60%. So whatever you had it set at, you can drop down to 60%. And really, that's been addressed a lot by ASHRAE. Folks are, say, hey, you got to deal with these VAV systems or multi-speed constant volume systems or multi-speed fan coils, and this is the reason why, okay? But what, for some reason, people don't seem to understand is that, there's other things that can happen here that affect the change in flow. In this case, I'm going to say, hey, the supply flow hasn't changed at all, okay, but maybe something on the exterior surface of that unit has, okay, and, what would that be? Well, it'll be wind pressure or it'll be stack pressure, okay? These are big deals. So then the next question would be, what kind of wind pressure do we need or stack pressure change do we need to see the same kind of changes on the intake system that we saw from supply fan speed changes? Okay, so we look at this again and we take a look at it, 2/10 of an inch change. Hey, where else do we get it? We get it with an 18 mile, basically going from an 18 mile an hour direct wind to an 18 mile an hour crosswind. So the direct wind is a positive pressure on that intake system, and the crosswind is a negative pressure on the intake system. And if you looked at this, you'd have about a 2/10 of an inch change. So that even on this system that we had, if we kept the supply flow constant, we'd still see this 40% change in flow. We'd actually have a 40% reduction in flow going from an 18 mile an hour direct wind to an 18 mile an hour crosswind. Okay, and so now when you take a look at this, that black line is the, what we'll call the fan speed changes only, the thing that people are used to seeing, okay? And now you superimpose on top of that the fact that we have wind pressure changes, so the direct wind or the crosswind. That means you can be anywhere between the direct wind curve and the crosswind curve. Now, if you look at this, the set point 100% is where you want it to be, that dashed black line. So there's going to be a case where you can be above it, and then there's going to be a lot of cases where you can be below it. If you're above it, you're going to have potential problems. If you're in a cold climate, you might see some coil freeze issues. If you're below it, you're going to have pressurization problems. You're going to most likely have an air quality problem. Well, you know what? This is a lot of your systems because you don't have active control in a lot of your systems. So take a look at that and remember that, okay? And then this is actually from our building where we actually took, actual data to kind of back this up. So when you take a look at this, we have the wind effect, and here we have it on a day when there's virtually no wind. Now there's not really a day when there's no wind, okay? So we have some wind going on. So we have, basically you have the scatter data there is what you'll see on an outside air intake, a little bit of turbulence because this is a close couple to the outside air intake. So a little bit of turbulence because of the proximity of the louver and the damper, but it's also small changes in wind speed and direction, okay? Now we come back on a day, we don't change anything, we come back on a day when we have a 15-mile-an-hour crosswind, okay, and we take the measurements again, and we had a 24% reduction in the average outside air. And the other thing I want to point out is notice all the scatter got greater. It's because when you have wind, people have to understand this, when you have wind on an outside air intake, particularly a rooftop unit, okay, you have wind that's kind of like 1 minute it's 15 miles an hour this way, and the next second it's like 18 miles an hour that way, and then it's 10 miles an hour that way. Well, what happens? You have a damper. You can't compensate for that. In this case, the damper's fixed anyhow. One of the problems that we see a lot of control folks do is they have the output of their control loops just too aggressive, too fast, and it'll actually make the system hung. You have to really understand how to do this. Slow down the output of your control loops. Look at the running average of the result, which is really what that red solid line is, but control the actual input data, okay? It's another conversation. We're not going to have it today. We could have it, okay? But the big thing I want you to get from here is just going from no wind to a crosswind. We got this major change and reduction in outdoor airflow. So if you're relying on damper position, or you have no way to compensate for this wind pressure, this is a large error, and this has nothing to do even with the fan speed changes, okay? Now stack effect's a whole other thing. People think of stack pressure and how it affects individual floors, pressurization of individual floors. What they don't always look at is that the return air duct's a big hole in the building. In this case, I have a unit on the roof, and it's serving the first floor only, so that return duct's a big hole in the building that connects the first floor to the downstream side of that intake damper. And when the indoor temperature and the outdoor temperature are the same, there is no stack effect. Okay, so you go and set that up, no big deal. But now you come back in the winter when the column of air outside of the building is so much more dense. Okay, so it's putting a positive pressure on the downstream side of that intake system. All right, and it will reduce the outdoor air that comes into the building, okay, period. And in the summer, it's the opposite. Typically, the offset in the summer is not as much as the offset in the winter, depending on where you are in the country. So summer stack problems aren't as bad as winter stack problems. But when you look at it, this is a 70-foot low-rise. This is not a high-rise. 100-degree swing, 0.2 of an inch, same problem we had. It would be a 40% reduction or change in flow. And that's not acceptable. And you might say, well, my climate's not like that. It's like, okay, so make the building a little higher if you live in San Diego. Okay? The bottom line is it's still a problem. Okay? And some climates are even worse. Okay? So that when you superimpose that, you look at winter and summer stack effect, you see some significant changes in, again, your goal is the black dashed line, and operationally, you're between the two red curves. That really isn't acceptable. Okay, and then of course, don't forget, the wind can blow when the temperature changes. So now we're just superimposing summer stack with direct wind, which is the worst case in that direction, and winter stack with a crosswind, which is the worst case in that condition. And you have no idea where you are. In fact, you could have turned your intake into an exhaust, which is really not that uncommon. And, honestly, we do this. I do this for balancers a lot because I want balancers to understand. Balancers do understand it, actually. But, I've been doing this with balancers for years and years and years, and it's like, you go out and you set up a system and somebody comes out and checks your work and it's very different. Is it because you didn't do a good job, or is it because something else changed? And in a lot of cases, it's something else changed. And you just cannot go, static measurements in one instance in time does not do the job, okay? You have to control this out, and you can control this out. If you're measuring this, you control it out, all right? All right, and I just throw this slide in just to think about it for folks. Some people say, oh, I reset the damper to compensate for fan speed, or it's a little bit different, but I use 2 damper positions for my DCV strategy. Keep in mind that everything I showed you is based on the flow coefficient of that intake. So if you go to a more open position, you've decreased the resistance of that intake system, meaning that the wind and stack pressure problem is even bigger. And you need to recognize that, because you don't necessarily see things operationally. Somebody goes out, sets it up, walks away, and you wonder why these buildings don't really work. Okay? The other thing we need to talk about is dampers. We have damper-induced problems, hysteresis, binding, and deterioration. Well, hysteresis is pretty simple to understand. I have a drive shaft, I bring it back to the same position, but because of slop in the linkage, all the other blades don't go back to the same position. That's going to change the flow. Binding, well, that's actually even easier to understand. If I have, how many of you that, if you've been in the field, you know what I'm talking about, damper blades binding because the bearing seize up, and in a lot of cases you'll even have the linkage break, you'll have damper blades not even move. Obviously, if you're relying on damper position, those flows are changing. And deterioration, I'm primarily talking about seal deterioration. You have one opening size with the seals brand new, you have another opening size with the seals deteriorated, okay? These are big deals, okay? All I'm showing you here is just data, again, from our building. It's just damper hysteresis. It's real simple. Which way did you open the damper? And if you look at the black line, we basically went from closed to 15% open. If you look at the red line, we went from open, like 100% economizer to 15% open. There's 20% variability there depending on which direction you came from. So you come from night setback or you come from economizer. Are you operating in a DCV mode going between a min-min and a min-max? I mean, you're not coming back to the same point. If you depend on damper position, you really are not getting what you think you're getting. Yet again, if you measure this, you can control it out, okay? So then when we look at all these factors that influence intake flow rates, there's a lot of them. You got the system effects from the fan speed variations. You got the environmental effects, the wind pressure, stack pressure. You got damper issues. You've got to measure and control this out, or you're going to have building problems. Okay? All right. So that's the end of this section. My next section actually is going to talk about different. At this point, I think where I would want you to be is that you have to do something to do control. I don't know that I necessarily think that you need to be at a position where you need to directly measure. So that's where I need to get you next. Okay. All right. Thanks. Be right back. Okay, hopefully the last presentation has convinced you that you need to control your outside airflow rates, okay? But maybe you haven't decided how you want to do that yet, so we're going to help you understand. Okay, we're going to take a look at calculated methods. Okay, what do I mean by calculated methods? Well, calculated methods are going to be, we're going to indirectly figure out how much outside air we have, flow rate we have. We're going to do it either with the temperature ratio method, which some people call the energy balance method or adiabatic mixing method, or we're going to do it with the delta CFM method, meaning we're going to take the difference between the supply and the return flow rates as long as we don't have any relief at the air handler. Okay, so we'll start with the temperature ratio method. So in the temperature ratio method, And this is in standard 111 basically. But basically, if I know the outside air temperature, I know the return air temperature and the mixed air temperature, I can theoretically calculate the percentage of outside air in the mixed air, which is essentially the supply air. And if I know the supply air flow rate, that percentage of outside air in the supply air times the supply air flow rate is how much outside air I have. People have been doing this for a long time. There's companies that actually promote this strategy today. And so the question is, does this work? All right, so we're going to take a very specific example first. This one here. It's 40 degrees outside, it's 75 degrees return air. It measures 71.5 degrees on the mixed air. But mixed air is very difficult to measure accurately, okay, because it's mixed air. It's mixing return air and outside air, and honestly, a 2-degree uncertainty isn't a lot of uncertainty. It's probably greater than that, is what I'm saying. So let's go ahead and calculate it out with that error. And when we calculate it out with that error, we calculate that there's 10% of the of the supply air is outside air. We measured 100,000 CFM, so we got 10,000 CFM of outside air. Okay, let's just go back and calculate that again, but not with the wrong mixed air temperature, with the correct mixed air temperature. And what we would end up getting here is 4,200 CFM, 4,286 CFM of outside air. This method's only 60% off. And that's if all your other measurements were perfect, which they're not, okay? So that's no good. Now, what people have said to me, which I know you're going to say this to me, it's like, you just took an example that, looks bad. It's like, no, I'm not going to do that. I've been doing this too long to do that. So listen, here what I'm doing is I'm going to hold that 2-degree uncertainty constant on the mixed air measurement. It's probably worse than what I'm showing you, okay? And I'm going to look at temperature from 20 to 100 degrees outside, and I'm going to look at percentages of outside air and supply air that range between 5 and 25%. I think that's a pretty good range for most of your applications, okay? When you look at this, that little green area is my plus or minus 5% target, where I want to be. Okay, you're nowhere near that target. In fact, the errors are huge. And, if your eyes aren't very good, you're looking at that and you're saying, well, is that 5 or 10? No, there's no decimal points. I mean, basically, these errors are running, 20 to off the scale percent. Okay? And it doesn't matter what the outside air temperature is. It's simply it's a bad method. It shouldn't be used. It shouldn't be in standard 111. And because it's in standard 111, it could be used by test and balance as a way to verify our equipment, which is a really bad idea too, okay? So I want you to think about that, but I really don't ever want you to use this method, okay? If somebody comes in and tells you they can use this method, I don't think you should. I think you should just pull this out and say, tell me what we're doing wrong here, okay? Because I think that you're going to find that it doesn't work. The other one that gets used a lot is this delta CFM method. I mean, I see it all the time, particularly now that there's so many fans with piezo rings in it. People are like, I just got flow measurement. How big a deal is this, okay? How much does the accuracy really matter? It's good enough. All right, well, in this case here, I'm going to show test and balance, but it could have been piezo rings. It could even be EBTRON in the ducts. It doesn't matter. I'm just going to, we're measuring flow, the supply and return. We have no relief at the air handler. The difference mathematically is the outside airflow rate. Okay, that is a fact. So here we measured 100,000 CFM on the supply, 90,000 CFM on the return. We think we have 10,000 CFM of outside air. So it's going to be like, okay, how accurate do you think you can do this measurement? And it depends on who you talk to. I mean, some people feel like they can get measurements within 3%. I know if you use EBTRON properly in the supply and the return inducted systems, within 3% is very reasonable. Okay, there's other folks that'll say, I'll get within 5 or I'll get within 10%. Piezo rings, if they're getting within 10%, they're having a good day. So, I'm going to use 3% just because it's on the lower end. It's probably as good as you're going to get, okay? So that means when I'm reporting 100,000 CFM, I could be plus or minus 3% of that. And so I'm going to look at, what if I was 3% less? That's what plus or minus 3% means. So when I reported 100,000, I really had 97,000. Okay, and return error, plus or minus 3%, what if it's 3% more? Again, that's what it means. So I reported 90,000, it's 3% more really, so it's 92,700. So that when I think I have 10,000 CFM, I really had 4,300. That's not any good. That's not acceptable. That's 60% off. That's ridiculous. So you don't want to do that, all right? And again, you're going to say, well, Dave, you picked a bad example. Well, I knew you were going to say that to me. So I look at, in this case, I actually even expanded the amount of outdoor air and supply air for folks that do this on healthcare. So I go 5 to 50% there of outdoor air, a percentage of the supply air. And I look at different accuracies of measurement, anywhere from 0.5% to 10. Okay, and in a lot of cases, the flow meters you're using aren't even repeatable to 0.5%. Never mind the potential for accuracy to that. You're not really getting down there. Okay, so you got 0.5% to 10%, and really none of them are acceptable. It's so bad that I had to plot the accuracy on that vertical left axis there. It's a logarithmic scale. I mean, it's off the chain. It's not, you can't do this. You're doing it, but you can't do it. You shouldn't do it. It's not a good idea. Okay? Again, if it's a method that's being used to check the EBTRON, it's not a good idea either. Okay? Now, that's indirectly calculated methods. Now, there's other methods out there where they have to be calibrated in the field. Okay? So, it's going to be dampers, obviously. We've talked about dampers. We beat that up. We've fixed in two-position dampers. It could be, dampers with reset. It doesn't matter to me. We've already talked about it. We'll just talk about it again, I guess. Mixed air plenum pressure control. We didn't talk about fixed orifice airflow measurement, where you're using the louver or something else as a fixed orifice in the intake system. And then, of course, you could always go out and put one of our products in with, 1 or 2 sensors, and so low sensor density. I don't even know why I put our averaging pitot array, because they shouldn't really be applied on most of your outside air intakes anyhow, but just because the velocities are so low. But these are methods we should look at. Okay, well, first of all, they can't be any better than what you're calibrating them to. So, if I have a rooftop unit, and I think any balancer would tell you this, rooftop units are designed so poorly that getting a good field measurement is often very difficult. Now, there's different techniques they can use, to maybe get this a little bit better, but if you're measuring at the intake on a rooftop unit, if you get within 25% of the actual flow, I think you're having a good day. It's mostly because of that intake configuration. It's just not designed to get a good measurement. The airflow rates are often extremely low, super affected by wind on the roof where you're taking these measurements. You might have used that method of energy balance method that Standard 111 talks about. You might be using a pitot tube or a valve grid or something, a differential pressure-based device at 50 or 100 feet per minute, and you shouldn't be using it there. And then you might not have a good balancer, but that's not really what the deal is. But these are the things I would identify as the problems. When you have the fixed minimum position intake damper, and you look at this, we've already talked about the problem of being, wind and all these things. So I'm just going to go through this quickly just to give you an idea of what I'm talking about. And I don't think I know. I have a little summary table. So in this case here, you have a fixed or multi-position damper. You're setting up the test and balance. This other system, method here, mixed air plenum pressure control, what you do is you go out with balancer, you determine what the mixing box plenum pressure is that you want to maintain a flow. You're either going to modulate a return fan or modulate a recirculation air damper to maintain that pressure drop over that system. Okay, so that's another method. The fixed orifice airflow measurement method is one of our competitors does that. They use the louver as a fixed orifice. So again, you're going to go out, you're going to have test and balance, because you don't know what the flow coefficient of the louver is, particularly in the installation that it's in. Okay, and in a lot of cases, you don't have enough points of measurement either. Okay, as is true here with low sensor density. You might say, hey, I don't want to put the high sensor density EBTRON in. I want to use just a few sensors. It's like, yeah, you can do that, but do keep in mind that there's velocity profiles. There's velocity profiles, and like on the previous slide, there's pressure profiles that create problems, and they're not necessarily the same from day to day or condition to condition. Okay, so I made this little table, and it's like it looks at these different methods and the things I'm concerned with. So I'm concerned with fan speed variations, wind stack pressure changes, damper issues. Do I want to do this at more than one flow? So turn down measurement, is something going to create my velocity profiles to change? Which is yes. I've got wind pressure. I've got, even though you don't think about it this way, recirculation air damper, depending on where it is, will change the velocity profile of an intake, as will the damper on the intake damper. And then the installed accuracy, that what I'm talking about there is, what's your reference, okay? So let's look at fan speed variations. And I think I'm being very, very liberal on this, how I look at it. Obviously, the dampers don't work. We already talked about that, okay? It doesn't matter if it's fixed or multi-position. Multi-position can do a little bit better with fan speed, but you're assuming damper linearity. You're assuming the damper doesn't foul up. You're assuming that there's no hysteresis. You're doing a lot of assumptions. Mixed air plenum pressure control, it's kind of like the same thing. You're making a lot of assumptions on the damper, but the reality of it is, you can make some, you can compensate a little bit for changes in fan speed, as you can with measuring the pressure drop across a louver, as you can with using a low sensor density airflow measurement device. They're not great, but you can at least make an argument, yeah, it's better than nothing. It's certainly better than fixed position dampers. When you look at wind and stack pressure, well, anything that just relies on dampers, you have no idea what's going on with wind and stack pressure, so that's out. And we'll give the rest of these the benefit of the doubt that, yes, they can compensate for it for some degree. When you get into damper issues, all of a sudden now mixed air plenum pressure control is out the window, because you're depending on a fixed damper position. So if it's not going back to that fixed damper position, or the seals change, or there's hysteresis, or there's or there's binding, you just don't know what's happening. You'll get to your mixed air pressure set point, but that doesn't mean you're getting the flow that you got during setup. I think you have a little bit better chance with the fixed orifice airflow determination as you do with the lower sensor density airflow measurement. Again, none of these are great. Turn down measurement, meaning I want to do different flows, well, these are out. Mixed air plenum pressure control, that's not how you're using it at all. I don't think it's really good for the fixed orifice airflow determination, because you'll find that flow coefficients actually do vary a little bit. So if you're relying on one flow coefficient, you're probably not doing very well. I guess you can do a calibration at multiple points and improve it. Low flow sensor density, yeah, I guess so. We're going to turn down the flow. We're going to definitely see some changes as a result of that. So it's the best of the lot. Changing velocity profiles, which I said that happens from, there's so many things that cause velocity profiles in an intake. I've seen 10-to-1 flow variations on an outside air intake, just by looking at individual sensing points of the EBTRON. And it's because of the way the louver's set up or the hood's set up. It's because of the way the wind's blowing. It's because the damper position of the outside air intake damper. It could even be the return air damper position. There's a lot of things that will cause the velocity profiles to change differently than from when the day you set it up, so that honestly, none of them work. Okay? And then ultimately, none of these can be any better than the reference, because you're calibrating all of these. You're not going to tell me, even down with a low sensor density airflow measurement, and I'm going to put a couple sensing points in an outside air intake and just be done with it. No, you're going to have to go out there and you're going to have to take test and balance, and you're going to have to adjust it, so nothing can be any more accurate. You know, it's limited by how accurate is that measurement. And on a rooftop units, it's probably pretty poor. Okay. So what we like to see you do, imagine this, is measure and control with a factory calibrated device, high sensor density, so that you're picking up these velocity profiles. Use a technology that's, you know, suited for low flows, you know, which is like the EBTRON, okay? We've tested EBTRONs and determined what position the EBTRON needs to be upstream of a damper so that there's no damper interaction, okay? So we've looked at these different things. So, you know, use properly installed and applied. Make sure that somebody's looking at it. Make sure they, I like to get the air balancer and the control contractor and everybody involved to understand, is this properly installed? Is it properly applied? You know, do you have something as simple as the area correct? Okay. But use the thermal flow meters that we make. I think that's a good idea, obviously. But, you know, and then with test and balance, you go out and you verify it. Now, what's the difference? Well, the difference is this. If I'm a test and balance person and I'm measuring in a duct and I say my uncertainty is 10% and the flow measurement's within 10%, you verify it. There's no need to make it match your reading if you believe your uncertainty is 10%. Same thing's true on a rooftop unit. If you think your uncertainty is 20% and the EBTRON's within 20%, you verified it. You did your job. You did the right thing. Now use the readings from the EBTRON, okay? That's what I'd like to see happen there. And so when you look at this same table, now you add another row for these high sensor density airflow measurement devices, all of a sudden you can deal with all of this. And that's a big deal. And so when you look at the standards and codes that support this, 62 doesn't do it the way I want to do it. It does it in Appendix L, which is existing buildings. It says measure system outdoor airflow measurements may be made directly or by installed flow measurement devices in the system that are calibrated. That's important. California Title 24 is the same thing. You know, ventilation airflow must be certified to be measured within 10% of the design airflow. If airflow monitoring stations are provided, they can be used for these measurements. Washington Energy Code requires some airflow measurement. LEED requires airflow measurement. There's others. I mean, we can go on and on. We're not going to. Okay. All right. So hopefully now, at this point, you've decided that, yes, not only do I need to control outdoor air, I need to measure it. And it's not just recirculating units. It's DOAS units. We haven't gotten into multi-zone DOAS units yet. But it's just, you definitely need to be measuring and controlling these outdoor airflow rates. All right, thanks. I'm going to come back and do something else. Okay, now we're going to do demand control ventilation. This section is quite a bit longer than the other ones. So just kind of hang on through it. We're going to start off with, you know, what is demand controlled ventilation? We're going to look at CO2-based DCV, which is what most people think of when they think of demand controlled ventilation. Then we're going to look at occupancy-based DCV, okay? All right, first of all, let's just, you know, the basic deal here is this. Demand controlled ventilation does make sense. We have a lot of the outdoor air is required to dilute contaminants and body odor from the occupants. And it's very much related to the occupants. So if you have a higher occupant density space that is full, you have one ventilation requirement. And then if that space goes to a much lower population, then you have a lot less outdoor air required. So it makes sense that you would want to reduce the outdoor air and not bring in the design outdoor air when the population's variable. Now, I will say this, everybody does this on high occupant density spaces. Personally, I think if it's a high occupant density space and the population doesn't vary very much, DCV is actually pretty risky. But Most of your energy codes aren't written that way. There's like, hey, if you got a higher occupant density space, you're going to do DCV, whether the population is constant or near constant or not. So we definitely need to take a look at this. Okay. Now we're going to look at what basically drives DCV, and it's going to be for most of us, it's going to be standard 90.1. You know, a lot of your energy codes are really built on 90.1, and in California, it's going to be Title 24, Part 6. Now, for the longest time, California Title 24, Part 6 and 90.1 were pretty much almost the same language for when it was required, but 90.1 kind of expanded the scope of DCV. I really don't quite understand that, because this happened during COVID when folks were saying, you know, don't do DCV. The 90.1 folks were like, oh, you know, we need to actually expand its scope. So it's not as clear cut. Like if you look at Title 24 and how 90.1 was written, it was always 25 people or greater per 1,000 square feet. Now when you look at 90.1, it's a little more complicated to figure out when you should or shouldn't be doing DCV. But at any rate, that's what's driving when you do it, but that's not what's driving how you do it. Okay, so DCV is defined in Standard 62, at least for those of us that are dealing with you know, outside of California's Title 24 Part 6. So what I want you to look at here on the left is really the definition, okay? And it says basically for DCV ventilation zones in the occupied mode, breathing zone outdoor airflow shall be reset in response to the current population. And, you know, a lot of you are doing CO2 ventilation control, but don't really understand how that relates to this requirement. So we're going to have to go through and take a look at that. I also will say that I've always had a problem with this occupied mode deal. It makes sense on single zone systems. Actually, the math works out really well on single zone systems, and it works really well on DOAS systems, but it doesn't work well on recirculating systems, recirculating multi-zone systems. I mean, because it implies that there's no outside air required to dilute contaminants in non-occupied zones, and there is, and yet that air is being, you know, basically brought into, recirculated into other zones, and if you actually sit down and do the math on it, you realize it's not right. But at any rate, breathing zone outdoor airflow shall be reset in response to the current population. So I always say to people, hey, you're doing CO2 DCV. If I tell you the CO2 level, tell me how many people are in the room, and you can't. So we're going to have to take a look at that. There's also a minimum requirement. It says for DCV ventilation zones in the occupied mode, breathing zone outdoor airflow shall be reset, shall not be less than the building component. So that, you know, it's basically a tabled value of based on the floor area. It should also clarify the requirement for pressurization. I mean, you can interpret it by looking at Section 5, but really it should say the floor component or that required for pressurization, whichever is greater. Okay, it doesn't clearly say that, and I think it allows a lot of people to bring the ventilation rates down below the exhausts, and you run some buildings negative, you create some IQ problems. I've even seen where people don't even pay attention to this floor component, and they just shut the outside air completely off. Well, you might have local exhausts, and you know, you're creating a negative pressure situation, which isn't great. Now, breathing zone outdoor airflow on the right there, normally when you use Standard 62, you're looking at the number of people in the ventilation zone during typical usage, but because of this requirement now for the actual current population, you really need to pull that out and put in the current population of the ventilation zone. It kind of makes Standard 62 into an operational standard when we're talking about DCV, okay? Now, California's a bit different. California doesn't get into this population requirement directly, Okay, so Title 24 Part 6 is all about maintaining CO2 levels, and it's about, currently at least, about maintaining CO2 levels 600 parts per million above ambient, which is often about 1,000 parts per million. Okay, so there are some differences there. Okay, now I think that gets us to the point where we need to ask ourselves, you know, for those, since so many people are doing this with CO2, and as you're going to see, Standard 62 has actually incorporated some language for CO2 recently. You know, it's like, why are we doing this? Because there's a lot of misunderstanding about why we're doing, what is the role of CO2? Like when you measure CO2, what is it all about? I mean, over the years, I've talked to a lot of people that say, oh, well, you know, CO2 is a measure of indoor air quality, almost like treating it like it's a contaminant. And it's like, well, it's really not. That's really not why we're doing this, and you really need to understand why it is that we're doing it. So to do this, like historically, I think we need to look backwards in time. I started with 62, 1989, but actually before 62, 89, CO2 was mentioned as a kind of like a high limit in the neighborhood of 2,500 parts per million, meaning that if it exceeded 2,500 parts per million, you probably had an air quality problem, you didn't have enough outdoor air. In 1989, when the ventilation rates for Standard 62 were increased, you know, basically there was a sentence put into the ventilation rate procedure that I think confused a lot of people, as well as there was an appendix put into the standard that talked about CO2 and ventilation. Totally got misinterpreted, but particularly by folks that are selling CO2 sensors. But there was a sentence in there that said comfort or odor, you know, body odor criteria are likely to be satisfied if the ventilation rate is set so that 1,000 parts per million CO2 is not exceeded. And people started setting things to 1,000 parts per million because manufacturers that were making CO2 sensors were basically saying Standard 62 said to do that. It didn't. It said exactly what it says right there. And at the time, the thought process was the outdoor CO2 level was closer to 300 parts per million than 4. And we'll get into this a little bit, where this comes from. In 1999, the language was changed a little bit, where it says comfort or odor, again, criteria with respect to human bioeffluents are likely to be satisfied if the ventilation results in indoor CO2 concentrations less than 700 parts per million above the outdoor air. And that's because really the outdoor air CO2 levels are not necessarily all that constant. They're closer to 400 parts per million, but you can find studies that show the CO2 levels, you know, maybe because of things like thermal inversions and things like that, you know, of 500-600 parts per million. So it really has to do with this differential, and you'll see why if you don't understand why in a couple slides, because it's nothing about it being a measurement of air quality or a contaminant. In fact, until recently, the IQ procedure, you know, which talks about different contaminants of concern, listed carbon dioxide as a contaminant of concern when the 8-hour exposure exceeded 5,000 parts per million or the 1-hour exposure exceeded 10,000 parts per million. That was removed in the 2022 standard because basically a lot of the air cleaning folks were reducing outdoor air so much that this CO2 levels were getting considerably higher in buildings, so that this was just simply removed. It's not that it isn't still true, it's just you're not going to find it in the IQP right now. Okay, so it's not a contaminant. What is it? Okay, so okay, this is one of these slides. It's a lot easier for me to do in person. I can kind of point around a little bit, and you know, doing it kind of virtually is a little trickier, but at any rate, we're gonna give it a shot here. So I always like to say to folks that you know, you mechanical engineers, which I am not a mechanical engineer, by the way, you mechanical engineers really weren't very good at chemistry, and I know that because my roommates were mechanical engineers in college, and chemistry was the class that was used to kind of weed them out. So the first thing we do in ASHRAE in looking at this, which is really not correct, is to simplify this relationship. We're going to make the assumption of steady state. And steady state just means that in this case, we've got outdoor air coming into a ventilation zone, and we got people in the ventilation zone. And at steady state, everything's constant. Okay, the number of people in the ventilation zone are constant, their CO2 production rate is constant, the amount of outdoor air flow rate, the outdoor air flow rate coming in is constant, and you'll get to steady state, which means that the CO2 level in the ventilation zone will actually plateau out. It won't continuously increase, okay? But anyhow, ASHRAE's used this relationship to kind of justify the use of CO2 for controlling outdoor air. And so let's just take a look at then what we're talking about here. So if you look at the left, okay, the left there, where it says outdoor airflow, CO times VOZ. CO is the concentration of CO2 in the outdoor air, and VOZ is the airflow rate. We're going to keep that constant because we want to create a steady state equation. So that's going to be one term in the steady state equation, okay? The second term in the steady state equation is going to be, we have occupants, okay? In this case, we have a fixed number of occupants and they're all producing CO2 at the same rate. So that basically we have the number of people times the CO2 production rate, or in this case I'm saying G times P. So G is the CO2 production rate, P is the number of people. That's dimensionally the same as the first term, COVOZ. So this is creating a valid steady state equation, okay? So those are the two goes intos, and what goes out of that space is then the same amount of the same rate of outdoor airflow that comes in is going to go out. It doesn't accumulate, but it's going to go out at the new elevated CO2 level. Okay, so instead of CO, we're going to call it CI for the indoor CO2 level. VOZ is going to be the same, so we have CI VOZ. So you basically have an equation there. It's a steady state equation, the ins equal the outs. Okay, it's really not what's happening when you're doing demand controlled ventilation, because the whole deal is you're changing the ventilation rate based on the occupancy. But that definitely complicates the math a little bit. So, everybody has just assumed steady state, which is, to me, it's a really big mistake, actually. But at any rate, we go back and look at this and we have this equation. It doesn't really do us much good. We can rearrange that equation algebraically. So it's still the same equation, but might provide us with something a little more interesting. And if we rearrange that, we'll find that if we know the CO2 production rate and divided by the differential between the indoor and the outdoor CO2 levels, that basically gives us VOZ over P, which in, at least here in the States, that's outside air CFM per person. Well, now you can go back historically and see, oh, well, this does make some sense a little bit here, because back in the day, previous to 2004, Standard 62 was 20 CFM per person for an office and 15 CFM per person for a classroom. And it ends up that 15 CFM per person is also the amount of outdoor air required to dilute body odor of a seated adult, which is the whole basis actually of California's Title 24, okay? Part 6 at least. It's based on diluting body odor. So when you take a look at this, you can now understand, and I realize that this is pretty small print if you're looking at this on a laptop, but that 700 parts per million that we talked about is basically, if you do this calculation out, use the CO2 production rate for sedentary adults or seated adults, we find that 700 parts per million is roughly 15 CFM per person. Okay, and that 15 CFM per person, then, all the statements about, hey, most likely diluted body odor is true, doesn't mean that you've met the requirements of the standard, and it certainly has nothing to do with CO2 being a contaminant or having good air quality. It just means that if you're 700 parts per million or less, you're most likely bringing in at least 15 CFM per person. Okay? That's what this is about, and it's very important that if you don't know that, which, I started doing this presentation in the early 90s, And back then, nobody really understood this. Today, I think there's a number of people out there that say, yeah, you haven't told me anything new, Dave. That's fine, but I can guarantee you there's plenty of you in the audience that are like, oh, I did not realize that's why we're measuring CO2. So the problem is, there's a lot of problems actually, but once you realize that you're measuring CO2, it's a proxy for outdoor air CFM per person, the next question you should have is how much uncertainty then is there in the amount of outdoor air that I'm bringing in. Just like if you were to put an airflow meter in the outdoor air intake, just because it gives you a number doesn't mean it's the right number. So it's like, well, okay, how much uncertainty is there in this measurement? If I say that a 700 part per million rise on seated adults is 15 CFM per person, is it really? Or is it 20? Is it 25? Is it 10? Is it 5? I mean, you want to know. So what affects that? Okay? And so what affects that is the accuracy of the CO2 measurements. So we're going to look at that. But what also affects it is you've made some assumptions on the CO2 production rate of the occupants. And basically that means that you've made an assumption, what affects that CO2 production rate is, well, the activity level of the occupants is extremely important. I mean, are you sitting down? Are you sleeping? Are you running around? It's a huge deal. We're going to look at that. The sex of the occupants. There is a difference between males and females in terms of CO2 production. The diet is it's not as significant, but it's there. Are you a high fat or a high carb diet? The ages can be significant. Are we doing this for a 5-year-old or a 50-year-old? And then the body mass of the occupants. Are we doing this for, a 100-pound child, or are we doing this for a 350-pound athlete? Okay, these all matter. And it's important to understand that. And then, of course, we've assumed that we're at steady state, but if we're really applying this to spaces that have varying occupancy, then we're not at steady state. So how much does all this have affected? So we're going to look at the accuracy in the measurements, and we're going to look at it the way that people are traditionally doing CO2 DCV today, meaning that they're setting 1,000 part per million set point in a space. And we're not going to worry about anything else. We're going to say, we know the outdoor CO2 level is 400 parts per million. We're just going to do that to make this easy. We know the CO2 production rate of the occupant. Okay, so the question then is, how much does the CO2 sensor measurement influence, what we're doing here? So when we look at the measurement error, it's like how much of the sensor itself has some inherent error in it. But what not a lot of people look at, and unfortunately I don't have enough time to put it all in here, but where's the sensor located? Okay, because you're really trying to get the average breathing zone CO2 level. And that's kind of affected by how the air is mixed in the space. And then on the outdoor side, unless you're using a really high performance and relatively expensive CO2 sensor outside, you're really not getting an accurate measurement, okay? So most people assume it's 400 parts per million. Some people measure it, but they measure it with sensors that really don't do a good job if the temperature is much different than room temperature. So, we need to take a look at that. So what we've got there on the graph on the right, okay, is that, we have, if you look at that red solid line, okay, the red solid line on the graph is how much outdoor air you would be bringing in if all your assumptions were right and the CO2 sensor had no error. Based on what we just said, it basically gives you CFM per person. So it's going to intersect down to 0. So that's the red line. I'm doing this for a classroom, and I'm doing this for, sedentary adults, okay, basically, all right? Now, the black line is how much outside air standard 62 requires. Now, I'll get into a little bit about Title 24 for you folks out there in California, but, the black line is how much outdoor air is required to satisfy standard 62. And you can, right off the bat, without even seeing any of this scatter, you can see that, okay, CO2 DCV is going to overventilate at the higher occupant levels and underventilate at the lower occupant levels. Okay, now what we're going to look at is we're going to say, okay, let's add some uncertainty to the measurement and do these calculations. So we're going to put 100 parts per million uncertainty in the CO2 measurement. And now the CO2 sensor itself might be better than that. It might be 35, 50 parts per million. It might be worse than that, okay? But where it's located is a big deal. Like at EBTRON, we have we call it our brain guest room. It's about 4,000 square foot. We have 12 CO2 sensors that are calibrated and match each other when they're together, okay? And then we have them all placed throughout the room, all at the same height. And when we load the room up, we'll see as much as a 200 part per million difference between those sensors. So that's sampling. It's not the sensor itself as much as sampling. So for me to say that there's 100 parts per million uncertainty isn't really stretching things too far. And in the outdoor CO2 level varying 50 parts per million, it can vary more than that, okay? So once you start to do that and you look at some of this scatter, you're like, oh, well, now it's not the red solid line anymore, okay? And this is just from the measurement error. This has nothing to do with CO2 production rates of the occupants, and it has nothing to do with steady state. We're going to assume all this stuff is going on. So what ends up happening on the higher end here, I'm going to look at the population all the way to the right, 35 students. You know, if we didn't want to be in CO2 alarm, we would be potentially bringing in 70% more outdoor air than the design called for, okay? Which means that your system really can't really condition that, and it may be great that you're bringing in excess outdoor air, but your system can't condition it. You probably, depending on where you are in the country, you know, can have temperature control problems, humidity control problems. You know, you might have pressurization problems. The thing is, you don't see this because when buildings are set up, you're typically not occupied, okay? So this is an operational problem that happens after the building is occupied, okay? And so it's very difficult to find these problems. You just have problems, okay? And so, you know, on the overventilation side, obviously it's wasted energy, which is not why you did this. You know, I mean, if I told you the airflow meter was 70% off on the outside air, you wouldn't use it, but you're doing this every day of the week. You could have thermal comfort issues. You could have pressurization problems on the lower end. You could have underventilation, pressurization problems, okay? All right, so, you know, what might you do, okay? You know, what you might do is say, well, I don't allow this to happen because I have a min-min and a min-max damper that I use for limit control. I either control at those 2 points or I use them for limit control. And that's fine, except that when we talked earlier about fixed dampers, we talked about all the uncertainties associated with fixed dampers. So, you know, that yellow area is your high limit uncertainty. So you really haven't accomplished anything. And if you have a variable speed system with a variable speed fan, it even adds more to it. So, you know, really, you don't know where you're at. And you don't see it during setup. It's an operational problem. It's not a setup problem, because during setup, you'll set these limits and you think you're where you need to be, but operationally, that's not what's really going on. Okay, so this total uncertainty is excessive. Okay, so the way you want to work through this is the best way to deal with it is do measured airflow limits. Okay, measured airflow limits then are going to keep you within the tolerance of the measured airflow rate, and this could be on an air handler at the intake, or this can be at individual ventilation zones of a DOAS system. Because these problems exist on all systems. It's not, you know, it's not just recirculating air handlers. It's not just rooftop units. It's, you know, this could be individual ventilation zones in a DOAS system. Okay, So you set these airflow limits. Okay. Now I said I would bring in the California Title 24 stuff. Yes, the ventilation requirements in Title 24 are different than those of Standard 62. Okay, but really you still have very similar problems. We have the overventilation problem, we have the potential underventilation problem, we have the fan speed problems, it's really not better. Okay. And so again, you're going to do the same deal. You're going to improve your DCV, CO2 DCV in Title 24 Part 6 by setting airflow limits. Okay. So the one nice thing is both Title 24 and new language to Standard 62 do allow you to be essentially in CO2 alarm if you can demonstrate that you've brought in the maximum amount of outdoor air for the design. So, basically on the left there it says zone and system ventilation rates are not required to be larger than the design ventilation rate required by Section 6.2. This is Standard 62 at design occupancy regardless of the CO2 concentration. Okay, and then if I go in here and add in what Title 24 says, it basically says the same thing. It's exactly the same language. Okay, so the thing is, how do you do it? It's really not hard. There's two strategies you can use. The one on the left is what I call deadband control. What's really going on here is that instead of setting a min-min and a min-max damper position when you want to be at the min-min, you're controlling to that airflow set point. When you want to be at the min-max, you're controlling that airflow set point. You can look at that logic. It's pretty straightforward. That's the one on the left. On the right, modulating control. In this case, so the one on the left is going to have two control points. The one on the right is just going to modulate between the min-min and the min-max. And if you're in the controls world, you'll look at that and you'll say, that's a control logic that we use on a VAV box for temperature control. The only difference is we've replaced the temperature, the first block there where it says measured CO2 level and CO2 set point. If you were doing a VAV box for temperature control, it would be measured temperature of the room and, temperature set point. But anyhow, it outputs a set point. In both cases, these have boundaries. Now, the beauty of this, and we haven't talked about IRMM, operation yet, but the beauty of this is that because you've integrated airflow measurement in it, when you're normally doing DCV, you're doing this modulating control between a min-min and a min-max. But if you got into something like a COVID again, and you said, hey, you know what, I want to disable DCV, you basically override the airflow set point. And this works great. And you might set it to design, or you might even say, hey, we're off peak load. We have the ability to even bring in more outdoor air. And I think if we did that during COVID, we would have been in a lot better place, particularly in schools. But we weren't in a better place because we didn't do this. And guess what? We've been out of COVID for a bunch of years now, and we still haven't done it. I mean, this is really the way to do DCV with what I call traditional, fixed set point CO2 DCV. Now, this is something you can consider because, and we started to talk about this maybe 15 years ago, all right? And so it still has some of the problems, it still has the problems of steady state in it, but what happens here is once you understand this relationship between CO2 and ventilation, you realize they're codependent, okay? And so we have one more piece of the puzzle and one more piece out of the equation, because now we're measuring the outdoor air, whether we're measuring it at the air handler or we're measuring it at the ventilation zone. We can now estimate the population, okay? And if we estimate the population, it doesn't matter where we're operating, whether we're operating in Standard 62 or Title 24. you basically can calculate the outside air required based on that estimated population. Now, it does have the errors that we've already talked about, and it does have the errors of steady state, which could be significant, but it is, in my opinion, an improved way to do CO2 DCV. In this case, the CO2 level will not be fixed. It'll vary. Okay, now we're kind of going to move on a little bit, and we're going to look at some other errors, okay, that we still have to deal with, and it's these metabolic issues that affect CO2 production rates. And it's a little bit unfortunate. I think Standard 62's tried to address this in a simplified manner, but if you look at the way this all came out, there was an addendum AB, came out probably 6 years ago. I kind of liked it. It kind of went through and calculated what the CO2 set point should be, and it didn't get approved. And then it got modified again and didn't get approved. And then finally, to make it easy, they made some table values that you can go back and modify to figure out, get close to what the CO2 set point should be. But I'm afraid nobody's going to do it. They're just going to look at the CO2 levels in the table. And when they look at the CO2 levels in the table, they're based on occupant default densities, and we're going to end up underventilating people, okay? Which I'm thinking was really the intention, okay? Because again, a lot of you that are energy folks sometimes lose sight of the fact that we're providing outdoor air for occupant health and well-being. It's not just about energy, it's about people, okay? And we seem to forget that. But anyhow, let's just take a look at this and see what happens here. So, first thing is, the first problem that we have when you're doing traditional, what I call 1,000 part per million CO2 DCV, what most of you are doing today, because you don't realize there's a codependence going on between the CO2 level and the amount of outdoor air you're bringing in. Basically, I've recalculated things out here for seated adults, 1.3 Met, based on data from the original addendum AB, okay? So 1,000 parts per million basically is approximately 17 CFM per person. Okay, that's what that means, okay? So that means that whenever you're at set point, if all your assumptions were correct, you're bringing in 17 CFM per person. All right, so now let's look at how you design, all right? You design a building based on, those of you here on, everywhere but California are, the code that you're designing to is really based on the ventilation requirements of Standard 62. So if I look at a classroom and, I look at the default occupant density, at design, it's 13 CFM per person. A lecture hall is 8 CFM per person. In a conference room or a meeting room or a worship space is 6 CFM per person. Okay, so you've sized your equipment for the design population at about these flows. Okay, but then you put a CO2 sensor in the room and said, oh, I also want to maintain 1,000 parts per million. Well, think about that. At the design of that classroom, you're designed for 13 CFM per person. But to get to 1,000 parts per million, you had to bring in 17 CFM per person. On a lecture hall, it's considerably worse. You designed it for 8 CFM, you're trying to bring in more than twice as much. And, so what ends up happening, I see it over and over and over, and it's more apparent in hot humid climates, because it presents a lot of other problems, okay, is that, these systems are under-designed or undersized. Well, what about those of you that are using the IQP and you're reducing the outside airflow rate, but yet maybe you're doing a school and the school says, well, I still want to be at 1,000 parts per million. Well, you've reduced the outdoor air, say, from 13 CFM per person to 8. Well, think about that. You're still trying to bring in 17. So, at higher load conditions, you have problems. You have temperature control problems. You have humidity control problems. You have pressurization problems. When I get into, Florida or areas that aren't using, economizers where they've sized the louvers for minimum outdoor air. They've got water carryover problems. I've seen EBTRONs look like chia pets, really, because they're just getting soaking wet. I've heard people complain, it's like, hey, for some reason all the return dampers are almost closed. Of course, you're trying to bring in more outside air than you design the system for. I've also seen and heard where people say, well, the equipment isn't working properly, or the engineer didn't design it right or size it right. It's like, no, you're calling for more outside air than you did design it for. You designed it for code, but now you're operationally asking it to do something else. So that's a big problem. It's not as much of a problem when you play with the 15 CFM per person number like California's Title 24 Part 6. In fact, it's really not a problem there, okay? But in all these other areas where the amount of outdoor air is significantly less than 15 or 17 CFM per person, it really is a problem. Now we're going to add activity level, and, we've got seated adults is what everything's based on, or 1.3 meds, that's 17 CFM per person. But just go from seated to walking slowly at 1,000 parts per million doubles the amount of outdoor air you'd be bringing in at 1,000 parts per million. Same thing. Look at go to vigorous workout. You're bringing in 103 CFM per person. You might say, well, I need more outside air, but you didn't design a system for that much outside air. So that's a problem. We've got age, 1,000 parts per million for an adult is 15 or 17 CFM per person, but 1,000 parts per million for a 5-year-old is 9. You still had to bring in that 13 or CFM per person or 15 CFM per person in California. You're not going to get there. You're underventilating those classrooms. You don't realize it. I can't say this enough. You don't realize this because you're not there looking at these buildings operationally. Okay, you're setting them up and then leaving, and then you're occupying the building, and then, oh, gee, we have all these problems. Yeah, we do. Okay, and this would be what the right set points would be. So these are problems. Okay, now those problems aren't going to go away. You can figure out what the CO2 set point should be if the spaces are all the same type of use and activity level. But, I'll run into people say, well, I have spaces that, sometimes there's seated people, sometimes there's people running around. It's like, well, you shouldn't be using CO2, okay? Because there's no way you're going to make that work. And then, we have the assumption of steady state, okay? And when we get into the assumption of steady state, here's the deal. You've assumed that that the number of people in the space and everything is constant, but the reality of it is it's not. You have people come in, then the CO2 level increases based on the volume of the space. People leave, then the CO2 level decays. You're not at steady state, okay? And so I put these things together for, those of you that are doing this traditional 1,000 part per million set point CO2 DCV. I'm doing a classroom here. We have 30, we have a classroom designed for 30, and it's got 30 people that walked in the beginning. I have different ways I can show this. I have different populations throughout the day, but I just want to keep this kind of simple. So they just come in, they don't leave. Okay. So they just come in, they don't leave. In this case, let's see if we can just take a look at this. The green is associated with the left vertical axis. That's the amount of outside air required. There's a dashed line there that is the time average, the real required outdoor air to meet the requirements of standard 62. The red is the amount of outdoor air you provided, and the dashed red line is the time average. So that's associated with that left vertical axis. The blue is the CO2 level that you measured. It's associated with the right vertical axis. A lot of people that don't understand CO2 and ventilation actually think that the best air quality was that first half hour because the CO2 level was below set point. It actually was the worst, right? Because you're bringing in a fraction of the outdoor air that you needed. It took almost a half hour before you got to where you were bringing in the right amount of outdoor air. Now, that may not be the end of the world. A half hour isn't too bad. But where the problem lies is on these spaces where you're bringing in, less than the design occupancy. So here's that same classroom that only has 10 students in it. And what you see is that the green, and the red, they're not together, okay? In fact, you never provided the ventilation required to satisfy standard 62. But the CO2 levels look great. So people that don't understand this would say, oh, well, the air quality was fantastic. Well, the air quality is not fantastic. You've underventilated everybody. You never got to the amount of outdoor air you needed. Okay, and then I've seen people apply CO2 DCV on an office. You should never do that. It doesn't work very well in low occupant density spaces. Here I've got 5 people per 1,000 square feet in this office. It's not even low occupant density. It would be worse if it was even lower. But I got 5 people per 1,000 square feet, and basically it took 3.5 hours before you brought in the right amount of outdoor air. It just shouldn't be applied on low occupant density spaces. So, does traditional fixed set point CO2 DCV comply with the ventilation requirements of standard 62? The answer is no, but you do it every day. Now, ASHRAE is, I try to deal with this and try not to overcomplicate it. And I understand that part of this, trying not to overcomplicate it. But we still have a responsibility to provide proper ventilation, okay? Especially after COVID. I just don't understand how we didn't learn anything from COVID. COVID, we still haven't recovered from COVID. Things are very, very different. Lots of things happened, and yet we're still so focused on just reducing ventilation. Okay, so so this was approved relatively recently, and it was added to the standard as a method for doing DCV, even though the requirement is still for provide the proper ventilation for the population. They've added this whole section on CO2 ventilation control. And, there's really no way for me to do this other than read it, okay? So it says DCV controls shall maintain the zone ventilation rate and no less than the building component, the floor area component. That's correct, but it should also say, or that required for building pressurization, whichever is greater, okay? That really should be added because this is just going to mislead people. When zone CO2 concentration is at C ambient, which is the outdoor CO2 level, which a building may or may not get to, okay? Upon a rise in the measured CO2 levels above C ambient, ventilation shall be increased proportional to the difference between zone CO2 concentration and C ambient. I should love that because even though I think the intent was just to reset some dampers, it won't work if you reset dampers. You basically put a flow meter in and you reset the airflow set point. Great. I should be running around pushing this. And I guess in a way I will be. Yes, the way you satisfy this is put a flow meter in and reset the outside air. There are problems with this whole strategy for multi-zone recirculating systems, but certainly on single zone, air handling units or DOAS, single or multi-zone DOAS, this works great. Just reset the outside airflow set point based on the CO2 level. Now there's an error here. It says when the zone CO2 concentration is equal to C max, the minimum zone ventilation rate shall be equal to its design ventilation rate. That is not necessarily even possible because of the codependence. It could happen, but you could get to a point where it can't happen, okay? Because there's a codependence between CO2 and ventilation. So I don't know, that shouldn't even be in there, okay? And then this informative note's pretty much kind of hits it right on the head. So they've added some CO2 levels to Table 6.1 in the ventilation rate procedure that talks about the ventilation rates required. And it says the CO2 values in Table 6.1 are only for the purpose of implementing CO2 DCV. They are not intended to be and should not be used as indicators of IQ. And my deal is then why is it there? But if you notice on the right there, you see the name of standard ventilation and acceptable indoor air quality. I don't know if you realize this or not, but before 2022, it was ventilation for acceptable indoor air quality. So what's the point? Okay, there's a big difference between ventilation for acceptable indoor air quality and ventilation and acceptable indoor air quality. And it ends up that if you hit some of these CO2 levels in that table, you won't necessarily provide the ventilation for the same row in the table for the same type of space. I think that's terrible, okay? And I don't even know what to say about that. I mean, I think that's terrible. So if you look at the table now, that all the way on the right there, they've added a CO2 set point. You add the outdoor CO2 level to that. So, you know, you got an office space. Well, that's 600 parts per million plus, you know, 400 outdoors, say, is 1,000. Reception area, 2,100 plus 400 is 2,500. I'm not saying that that the CO2 level shouldn't be higher, because when you look at it and you look at some of the stuff we just talked about, that yeah, they should be higher, but people are just going to set those CO2 levels, even though in the standard it talks about, you know, modifying them for the actual population you have. Nobody's going to do it, okay? So when you look at this, okay, what it's really saying, it's just a simple proportional reset. It's very easy to implement, particularly with an airflow meter, okay? When you look at the results, you'll find that it has a tendency to overventilate. So if we look at that graph on the left, okay, you know, the solid black line is how much outdoor you needed for standard 62. The dashed black is how much you would have provided. So you overventilate at the midpoints. I'm okay with that. It's actually going to it's going to help a little bit on the lag problem. But also notice the CO2 level varies. There's no, you know, it's not a fixed CO2 level. So I have some comments here. You know, yeah, accomplish this by resetting, you know, the outside airflow set point based on the CO2 level. I like that. But, you know, the biggest problem I have with this is my bottom little bullet there. There's no way to know if this is working operationally. I mean, the CO2 level is going to vary between outdoor, say 400 parts per million, and whatever design was, and you walk into a space, you look at the CO2 level, you're going to have no idea. You know, am I bringing, the only way you would know if you were bringing in the right amount of outdoor air is count the number of people in there and measure it. So I think we're even, in some respects, we're worse off than we were. There's no way to validate this, okay? Operationally, it's going to be a mess, all right? What it does do is it doesn't do much on the high population density. It doesn't really do anything in the high population densities. We still have about that point, you know, half hour on that 30 student classroom with 30 kids in it. But where it does make a big difference and helps the lag problem out is on the lower occupancy. So when we go back to that 10 students in the 30-person classroom, where when we did your traditional 1,000 parts per million set point, you really never got to the ventilation rate required. Now you actually got there immediately, and at least looking at time averages, and you overventilated. But that's okay. I mean, there's really nothing wrong with that. So that is an improvement on the lag problem, okay, or the steady state assumption. This is that office space again. I don't understand, you know, it's no better than 1,000 part per million set point. I don't understand why there's even a CO2 set point for an office space. It should be NA. It's not applicable. You should never use CO2 on low occupant density spaces. It shouldn't be there. You will never meet the requirements of standard 62. You'll never meet those ventilation rates. It shouldn't be there. People shouldn't be telling you to do something that doesn't work, okay? Now, when we go back and look at this again, you know, this is we've already looked at these slides. It's just a reminder. It's like, hey, this language is still there. Breathing zone outdoor airflow shall be reset in response to current population, and you know what that means. So that allows us to not. We can get our heads outside of the CO2 thing if we want to. Okay. So because the requirements are for the current population, there is now in Standard 62, and you know, talks about the CO2 control strategy, but there's an exception, and the exception is other DCV control logic shall be permitted to be used where it can be demonstrated to comply with Section 62611 under all expected operating conditions. Well, the best way to do that is going to be, you know, measure the number of people. Now, there's lots of different spaces out there where you can measure people. I mean, you can measure the occupancy of people going through the door. There's technologies available. We have one. There's other people that make them. That you can measure how many people are in the room. I always tell people with things like movie theaters and stuff like that, where you have a point of sale system, tells you exactly how many people are going into the movie, when it starts, when it ends. Yeah, tie that data into, you know, measure the outside air and set the set point. There's no lag problem. There's no uncertainty problem like you have with the CO2. Just measure the people. You know, we should be putting a lot of effort into this. You know, you want to save energy, great. And that's one great way to do it. And when you look at the errors associated with counting, I got a plus or minus 3-person counting error here. This looks a lot better than those other slides I showed you with all the scatter on it. I mean, really, you can have some error in counting and be significantly better than what you do with CO2 DCV. The other thing is, and it's outside of the scope of today, is if you were actually measuring the number of people, particularly in zones, I still use the old word critical zones, you know, you could calculate the ventilation efficiency in real time, and you can make decisions on getting the ventilation efficiency closer to 1, and you can make multi-zone recirculating VAV systems very attractive operationally, because you're doing on-the-fly real-time ventilation efficiency calculations. And I'd really like to see us, you know, spend some time looking at that, because there's some significant advantages of that, particularly over what we're doing today on VAV, where VAV today, you're looking at worst case ventilation efficiency. You have to oversize the system. You're bringing more outdoor air than you need. In a lot of cases, that gets people away from VAV, and you know, there's no reason for that. There's ways to pull this off. All right, so I told you that was a little bit longer. You know, it's the longest segment, I think, in this presentation series. So you know, when we come back, I'm going to talk about how to control things. Okay, now it won't be as detailed as some of you may like. It's a matter of time. All right, but we're gonna talk about that. All right, see you in a minute. Okay, now we're going to talk about controlling things. You know, making the buildings function better. And there's a lot of different strategies we could talk about. I could certainly do outside air flow control with building pressure using static pressure, and but that's not what I'm going to do. I want to do all airflow control because I have a limited amount of time, and I actually like all airflow control, meaning that we're controlling outdoor air, you know, flow rates based on measuring it, and building pressurization based on measuring the pressurization flow. We're going to look at recirculating air handling systems and dedicated outdoor air systems. Okay, so let's just take a look quickly here. The idea is really to create a pressurization flow, and that's only can be created by your mechanical system. Okay, so you know, on the left, supply relief systems or DOAS systems, it's pretty simple. We got an in path and an out path. We need to measure the ins and measure the outs, and you know, The ins are going to be based on, are going to be our ventilation for air quality, and the difference between the ins and the outs is going to be our pressurization. We might have to consider how we handle toilet exhaust, whether we do it. Typically, we'll do it on fan status. You're not going to measure every toilet exhaust in the building. But there are cases in high rises and things like that where we have to get a little more creative on where we're measuring, some of these exhausts. But at any rate, typically, this is what we're looking at here on the left, supply relief and DOAS systems, okay? And you always want to locate the flow meters in the best path you can, best straight run you can, and the cleanest air you can. I see people put things in the outside air intake on a DOAS unit. It's like, why don't you just put it on the supply side? It's the same flow. Now, when you get into recirculating systems, they're a little more complicated because you have that recirculation path. And I'm showing you there that we're going to do supply return and outside airflow measurement, but I want to show you why, okay? So this is a recirculating air handling unit, all right? And, technically, the mechanical ins and the mechanical outs create the difference between those two, create a pressurization flow. And a lot of folks think, well, that's what I want to measure. But it ends up that the outside air path is typically not the greatest to measure. It's fine if it's a ducted intake, but, we have a lot of rooftop units, and rooftop units are less than ideal. You can get 5% of flow on a good one and 5 to 10% on marginals. And, that's not good enough for differential flow control. Relief air, same thing. It's like, I see people measuring relief for exhaust air at the air handler. You'll get numbers, but the fact of the matter is there's a lot going on. It's less than an ideal location to measure the airflow rates. So the question is there another place we can measure? And the answer is going to be yes. And it's really easy, but I like to go through this little proof anyhow. So you see I got a little red dot flashing there. And basically what we can do is we can create an equation that says, hey, the supply airflow rate is equal to the recirculation airflow rate plus the outside airflow rate. And that's that first equation I got up above there. And now I look at this point here and I can say, hey, the return airflow rate is equal to the recirculation airflow rate plus the relief airflow rate. I have two equations, okay? I subtract those two equations, I still have an equation. So outside air minus relief air, which is what you want, is also equal to supply minus return air, okay? So they're equal, and that's great. So you really, you need to get your head around, I'm going to measure supply and return airflow rates, but also get your head around that anything you do that for fan or flow tracking, if it's sloppy or using not accurate measurements, going to affect that pressurization flow, ultimately can affect your building pressure, okay? So that's something that you need to think about. We could go through, different scenarios, what's wrong with riding fan curves, or what's wrong with using piezo rings, or whatever. But the bottom line is that differential is your pressurization. Okay. Now, if I'm doing this, and I seem to never even get to do this the way I want to do it. I have a sequence of operations for everything, but I'm not going to be able to do it today because I don't have the time to do it. So this is more like showing you where you're going to measure and then kind of verbalize through your strategy. But honestly, you need my sequence diagrams to really get where you want to get. Okay, But if we have a recirculating air handling unit and it's basically serving a single pressure zone, okay, then we're going to measure supply and return airflow rates. That's going to be our pressurization, and our outside airflow rate is going to be our dilution ventilation for air quality. Okay, I'd like to say that if you are doing a rooftop unit, you got to be careful about minimum flows, and it's not because of limitations of the flow measurement, particularly thermal. Thermal measured down in still air. That's not really the problem. It's that as the flows get too low on a rooftop unit, you are going to end up getting some false readings from wind gusts and wind blowing, and that's not really a good thing, okay? So we always use as a guide, try to keep the minimum airflow velocity at about 150 feet per minute or higher. It's not always doable. There's things you can do to improve this. Get to a lower flow. Basically, moisture eliminating screens are dampen, are mechanical wind dampening filters, as are regular air cleaning filters. And, there's a lot of outside air intakes I really encourage people to think about using filters on, because the outside air is so filthy. Okay, I mean, if the outside air is so filthy that when you look at your outside air intake a year after you install the unit and it looks like a chia pet, you got to ask yourself, do you really want that air coming in the building to improve air quality? Okay, and in certain environments, you get accumulation of material on that intake that accumulates on the sensors, and it causes some problems. That problem goes away typically with maintain moisture eliminating filters or air filters. Okay, I actually like washable air filters. But at any rate, think about this lower limit. Okay, now once we do see this once in a while, and again, it's going to be a little tricky to do quickly. Okay. But once you've decided that you're going to do this flow, you're essentially using the supply and return flow meters for airflow tracking, okay? And, if you try to do flow tracking and outside air control at the same time, and you have no relief at the air handler, okay, you end up having conflicting control loops, and they'll hunt. Because the differential between the supply and the return, even though mathematically is the same as that outside air, just small instrumentation error will make it so that those two numbers they're not the same. So that you'll end up with, with hunting, and you don't want that, okay? So what we do, and again, it would be nicer if I could take the time to show you the sequence. But we basically, when we have a supply and return fan system, we don't even use the supply and return flow meters when there's no relief. We just use the outside air flow meter. And we sequence, the return air fan is part of the sequence with the outside air and the recirculation air damper. Again, you can't see it here, but I can easily show you if you're interested. It works pretty well. When you're relieving air, now in this case we're relieving air because the outside air exceeds the pressurization, we're not necessarily economizing. Basically what we're doing is we're modulating those outside air and recirculation air dampers, preferably in sequence if we can, to maintain the outside air set point, and then we're controlling this return fan to maintain a constant differential, which is used to maintain the pressurization flow, okay? When we're economizing, it's very similar, except in this case, the outside air and the recirculation air dampers are modulating along with a cooling coil to maintain the supply air temperature set point, okay? And the pressurization is maintained by the differential between the supply and return flow meters. The outside air is only really there as a low limit. If we get into a real cold climate, we got to watch that the outside air doesn't go below the minimum, and if it does, we have to switch into minimum outside air mode. Okay, so that's how that goes along. Some of you might be asking, what is that optional DP or bleed sensor that you show? We like to decouple the relief air damper and open or close it based on a positive pressure or positive bleed airflow. EBTRON makes a bleed airflow sensor. I like it better than using a DP sensor, but they both do a very similar thing, okay? When we have a supply and a relief fan, okay, there isn't really much different in terms of the measurement points. If there's no relief at the air handler, obviously we can't make the return air fan our friend and use it in our sequence. We're just modulating the outside air and recirculation air damper. typically don't do much of anything when there's no relief with the supply and return flow meter, okay? When we start actively relieving, it's virtually the same thing as a supply return fan. We're using the outside airflow meter with the intake and recirc damper to maintain the outside airflow set point, and then we're controlling that relief fan to maintain the supply return airflow differential. One of the nice things about doing this with flow measurement is you'll never have that situation where you're bringing in outside air and it's short-circuited back to the relief. Because you're controlling these flows, it is going to work. Okay, and again, just like supply return, it's exactly the same, except we just have supply relief. When we get into systems with a separate relief fan, I do like to caution people, this is hard to do unless you really pay attention to the outside air and relief air paths, because you need accurate flow measurement for the differential. In a lot of cases, the outside air, if it's a rooftop unit, you don't have enough, you're not going to get the accuracy you need for good differential flow control. And the same thing's potentially true on the relief fan side. You got to look at the ducting, you got to properly apply the flow meter, or you got to pay attention to it to get the accuracy you need to do differential flow control. This is something that we see. Maybe it's a little more specialized. Maybe this is a system where we have a water side economizer or something like that, and we have a makeup air unit serving minimum outdoor air to multiple air handlers or fan coils. I kind of try to get everything out of one slide. Slide looks pretty much the same. This could be a VRF system with multiple fan coils, or this could be larger, individual floor air handlers. Okay, at any rate, we want to measure and control that outside air to each one of those either fan coils or air handlers. And a lot of you use like DP kind of flow cross rings or whatever you want to call them. And it's like, listen, we make products for this that are much more stable. And the fact is it's clean air. These units will last 15, 20 years, and not really require any maintenance or any calibration. You should really think about it. And it's not going to break the bank because they're application specific. Most of these ducts are relatively small, so we have products for that. Multi-floor central station systems is my least favorite system, because we have multiple floors that we have a big old return duct, which is a big old hole in the building, and when we don't control that return air, if we don't control the flow differential onto and off of each floor, we can end up with some real pressurization problems from stack effect. So, what we like to do here is we like to maintain a differential on, the flows onto and off of each floor. Don't sum up your VAV boxes to get the supply flow. It's not accurate enough to do that. Put a flow meter in the total supply. It might be more than one flow meter. Put a flow meter in the returns. It does require some kind of ducting or stub ducts. Our IQ product is actually pretty good for the return side. But you get this flow differential. You may have to change this offset throughout the year to compensate for stack effect and vertical leakage of the building, but you can pull this off. Okay. Otherwise, you just can end up with a big mess. I mean, I've seen plenty of buildings with an air handler on the 20th floor serving 20 floors above and 20 floors below, and they have some serious problems. Okay, so think about this in ways that you can improve the system there. Again, all I'm doing here is moving the return fan to a relief fan. Dedicated outdoor air, particularly dedicated outdoor air that is DCV. Okay, there's some things that you really need to think about, and ASHRAE has a design guide for dedicated outdoor air systems. But basically, for whatever the reason, when folks start doing this, they start thinking they don't need to measure or control flow. It's more important to measure and control flow. Not so much from the amount of outdoor air that you're bringing in, but for pressurization, okay? Because you've taken, and a lot of times when you're doing energy recovery, you've taken the air that you normally would use to pressurize the building and you're trying to recover the energy from it. So your differential is pretty small, your pressurization flow is really small, your margin for error is really small. Okay, so you should be maintaining the differentials between the outside air and the exhaust air. Okay, bare minimum. Okay, you should be doing that. All right, and there's other things you can actually pick up when you're doing this, depending on the type of energy recovery it is. If it's, if it's decimal wheel stuff, I mean, you can pick up from our stuff. You can pick up temperature, and you can pick up dew point or enthalpy or whatever it is that you want to look at. So there's a lot going on there. But it's bare minimum what you should do. If you get into multi-zone, particularly multi-zone DCV, okay, you should treat multi-zone DCV DOAS system like you treat a VAV system. You basically control the airflow into each ventilation zone and maintain it between a minimum and a maximum. Okay, and so it's very important that you do that, and it requires good measurement, and we have products for that, so that you do this at the individual ventilation zone level. You control the outside air fan, basically the duct static, just like it was a supply side of a VAV system. You're going to end up with a much better operating system. Okay, so in this case here, I have a redundant flow meter. The redundant flow meter is on the outside air. It just might be because of the way that you package the system. You might just want to have the flow meters all in the DOAS unit. But you can also, if you're using high enough quality flow meters like ours, you can just sum the total outside air individual ventilation zones, and you're going to get the same result. Okay, when we get into more humid climates, this might sound crazy, but it's not. As you change individual ventilation zones, on the supply side or the outside air side, you don't really pay that much attention on the exhaust side. You can make some of these spaces negative easily. Okay, and so that when we get into some areas particularly the deep south, it's like, listen, you should really consider doing some kind of flow tracking at each ventilation zone. Again, particularly when you're doing DCV. I mean, it's really when you're doing DCV I'm concerned the most about it. Okay, so, you should be incorporating these flow meters in, remembering what we talked about the DCV stuff and the different strategies you can use, and using the flow meters for limit control. And you're going to end up with a lot better operating system. And per square foot of floor area, you're not adding that much to the cost of this system. I mean, if this system doesn't work, then you've wasted a lot of money. So you got to do things to make the system work. All right, so that was my really quick version of control strategies. We can certainly talk more about it if you're interested. All right. Okay. When I come back, we're going to talk about EBTRON products, and then we'll be done. Thanks. Okay. Well, we just covered the first 4 of the 5 of these. I didn't do IRMM operation because, quite honestly, I've run out of time. It wasn't a lot of slides. I kind of talked about it a little bit with the DCV stuff. But we're now going to move into why choose EBTRON. And, basically, the big thing is we've been around for over 40 years. And, I've been there for 40 years. A lot of folks I work with have been there for a long time. I mean, we consider newbies to be people who have been around 25 years. Anyhow, we've always been really interested in performance, you know, making sure that we build a product that does what it needs to do for you. We've always maintained our quality levels. And for the performance and quality, we believe we have some really good value, okay? So we're certainly not the cheapest people out there, but it's not because, you know, any other reason. And we have to get the performance and the quality you need, we have to do some things to the product to make it work. You know, we're at the end of this, but we started in 1983. We pioneered direct outdoor airflow measurement in 1989. We've been using this thermal dispersion technology that I'm going to talk to you about since 1983. We put a lot of effort into our manufacturing facility and we build all our own test equipment and calibration equipment, and we're just different than everybody else. When you look at thermal dispersion, one of the reasons that it's really great for HVAC, it's there on the top in red. It's got more sensitivity as the flow decreases. That's really what makes it great. Most of our HVAC applications are lower airflow rates. We're not measuring airspeed on an airplane. So, you know, the lower the flow, the more sensitivity, that's a good thing. You look at vortex shedding, they have limitations, you know, under, 350, 400 feet per minute. So there's issues there, particularly for outdoor air intake, but also some tracking applications. And when you look at pitot tubes, pitot arrays, the air wings, piezo rings, all these other DP devices, they're exactly the opposite of an EBTRON. The sensitivity decreases as the flow goes down. So when you get to these lower flows, you get very little change in signal, yet you're using pressure sensors that are percent of full scale accuracy, so the errors are really, magnified. Okay, now how the EBTRON works, this is kind of like a simplified version of it, but it's what you really need to know. Each sensor node, or each sensing point, has two thermistors at it, okay? And if we can measure the power and the delta T, we heat one of the sensors up. If we can measure the difference between the heated sensor and the ambient air temperature, know the power dissipated airstream, we have a relationship that's proportional to velocity or mass velocity, okay? And that's really how it works. And for us, we've always selected this beam glass thermistor. It is the differentiator with EBTRON. It's not something that you just go and get involved with if you don't understand it. They're designed first of all, they're a handmade part. They're designed to survive extreme temperatures. They're hermetically sealed for long life. They can handle rapid changes in temperature on them. One of the big things with them is they're oven aged for stability. Your thermistors that you use in wall stacks and things like that, they're the only common ground between ours and theirs is the word thermistor. I mean, they're not the same thing. Chip thermistors are not instrumentation grade thermistors. Okay, so we oven age these things and makes them extremely stable. They're very variable though. We have to take each one of them and put them into multiple circulating baths that we maintain at 0.05 of a degree to get the resistance temperature characteristics so that we can determine the heated temperature, body temperature, and the ambient air temperature. And then we do some potting to make sure that they're properly sealed so they can handle salt water and atmospheric gases. One of the things about thermal flow meters is that, or a lot of airflow meters, but but particularly thermal devices, they definitely need to be calibrated. So the question is, what do you calibrate them to? And we just send our calibration standard to NIST, the National Institute of Standards and Technology up in Gaithersburg, Maryland, and we get a reported calibration, and that's a good starting point for us. We basically then transfer that calibration to our production tunnels, and we individually calibrate each sensor node. So each individual sensor node, if you have an EBTRON that has 16 sensor nodes in it, each one of those sensor nodes has gone through a calibration. For instance, our Gold Series, which is what I'm showing here, will go through a 16-point calibration from 0 to 5,000 feet per minute for the ducted units. Okay, and that gives us the ability to be a percent of reading device. I talked about the potting that we use. It's very important that people realize that outside air intakes are dirty, so they have to be able to survive, salt water, sulfuric acid in the atmosphere. So we go through a lot of testing and to make sure that these products will handle that. When the sensor's calibrated, kind of a hard screen to see again. But if you did a report of calibration on the sensor there on the left, you'd find that the typical EBTRON sensor node is well within 1% of reading to what it's calibrated to, typically even better, considerably better than that. And so that's extremely important in the overall process. Once these are calibrated, again, I'm showing a Gold Series probe, but it's very similar from product to product. We put the sensor nodes into the probe. There's a barcode associated with each one. They're scanned in. The sensor calibration data is written to a one-wire serial memory chip in the connector. So the devices are all plug and play. When you connect it to the transmitter, that calibration data is transferred over. Operationally, the transmitter is really reversing the calibration process. It's converting voltages to binary. It's calculating the temperature and the airflow and then outputting it, averaging and outputting it. It's pretty straightforward. We also have features that I don't think enough people use that come with pretty much almost every EBTRON except one version of our X1000, the analog version of it. We have velocity weighted temperature. So if you look there at the left, and it just is a very simplified way to look at it, but if I have air flowing at 5,000 CFM at 80 degrees and 2,500 CFM at 70 degrees in the bottom of the duct, you can't just get to take the average temperature. The average temperature would be 75. It's not 75. I have twice as much air moving at 80. It's really 76.7. Well, we weight each flow measurement point, okay, the temperature by the flow. So we give you velocity weighted temperature. Okay, so even if each sensing point was seeing a different temperature and a different velocity, you'd end up getting the true velocity weighted temperature of that airstream. We also use that, we add a humidity sensor, and from that humidity sensor we can get dew point. From dew point we can calculate out velocity weighted humidity, we can get velocity weighted enthalpy, and of course we can get dew point. Okay, so that's an option, but it's a small option add on the EBTRON. Okay, I think it's really great for enthalpy measurement. There's a lot going on in this little slide, but you have an outside air intake and you're doing enthalpy switchover on economizer. I think using the EBTRON is a superior way to do it. Okay, when we get into the products themselves, our reps are really pretty good with the products, so I don't have to spend much time here. The Gold Series is what we sell more of than anything else, and it's basically it's probes that can handle a total of 16 sensor nodes and several configurations of it. And basically in HVAC, we don't have a lot of room to measure airflow rates. So typically more sensors is better out of the box accuracy. So that's what the Gold Series is. We have something called a Hybrid Series, which is lower sensor density. It's the same sensors. It's calibrated the same way. And the bottom line is just less sensors. So that, if you don't have as much of a straight run or you're on an outdoor air intake, you're going to end up with potentially more error on the hybrid, say, than the Gold Series. We have plenty. Connectivity we got you covered. Okay, I mean we don't want to go through this slide, but we have isolated analog outputs. We have RS-45, which is field selectable between Modbus or BACnet. Same thing with the Ethernet. We have a dual Ethernet card. there's a couple of reasons for it. It can either be configured as two Ethernet connections, which makes sense with one of our with our smart display, but it's also an Ethernet switch for daisy chaining. We keep LAN on board, but there's not a lot of LAN application anymore. Mostly from a service perspective, I guess, is why we keep it. We have a USB data logger option where you can actually log airflow rates and temperatures. The Gold series has both the fans and the ducted probes have a low energy Bluetooth radio on it that works with your phone or tablet to give you some information. I'll show you in a couple minutes here. And then we have something called the IQ Enforcer Smart Display, which we'll get into. As for the low energy Bluetooth, it's a great tool. We don't charge for it. You can go in and you can get whatever you would see on the display on your phone. It'll tell you if there's any flow alarms that you've set internally that are active, or if there's anything wrong with the unit, trouble alarms. Okay, if somebody went and adjusted the EBTRON, you can see that they have, and you can turn that off and see what the actual unit read from the factory. We have a traverse data screen, which basically gives you individual sensor node data for airflow and temperature. It'll also give you the humidity sensor if it was connected. And then the other one that's really valuable is the diagnostic screen, which will tell you what all the parameters are set to. It'll go through, it'll show you any historical trouble codes, active trouble codes. It's great for field people. They just click the Send to EBTRON service button, and it'll email that file to EBTRON. And so that when you call, our service department has everything in front of them. Okay. We make some application-specific measurement devices. So you might have small rooftop units, and you're like, hey, I can't put a Gold series on it. I get it. So we have these EBFlow devices. They're also good for desiccant wheel measurement. On desiccant wheels, it can be configured so that it shows the airflow from the intake and exhaust side instead of showing airflow and temperature. We make a terminal box type unit that's great for VAV boxes, but it's also good for small flow tracking applications, labs, clean rooms, healthcare. It's great for dedicated outdoor air ventilation zone measurement. Okay, so you've got lots of products there. We make something called the bleed airflow sensor. It's a bi-directional airflow meter, half-inch airflow meter. Be honest with you, I can spend hours talking to you about how to use it, so I'm not going to do it today. Again, connectivity-wise, I think we have you covered. When we get into fan measurement, we'll do your traditional single dual inlet fans. We'll do your fan arrays. These flow meters do not affect fan performance. We can demonstrate that to you if you question it. If you don't believe us, we can show you why and how it works. Again, good connectivity, same connectivity as we talked about before. I guess I threw these in. I didn't realize I actually did that. This is a plenum fan with nothing in the inlet, and it's showing you what a flow meter reference downstream, ducted downstream of this unit reads. So, and what the current draw from the drive is in the sound level. So we'll just go over here. We've got the fan, nothing in it. We have the motor drive that shows 13.8 amps. And what our fan speed was set to, in this case, was 83.3%. The total supply airflow was 10,250 CFM, and the sound level was 90 dBs. We put our fan inlet unit in, and really nothing changed. Okay, the current draw is the same, the flow is the same, and the sound level is the same. Okay, if we put something like a pitot array in, and to be fair to the pitot tube, if we put what we call a throat-mounted EBTRON in, we'd have similar situation. Current draw goes way up, the supply flow goes way down, the sound level goes way up. All right. Bottom line is we don't affect these fans. All right. When you get into fan arrays on the EBLink, the low energy Bluetooth device that we have, basically we have one more screen, which is the individual fan. All right. So something new in the last couple of years for us is we call it the IQ Enforcer system. That's not new. We had that years ago. It's just it's really this version of it is a smart display. It's we don't need to go through the hardware, but it's basically it's a 7-inch diagonal capacitive touchscreen, same as on your phone. It's got a lot of horsepower behind it. This version of it you connect to our products using standard Cat 5 or higher cable. You do it as a separate network, so it doesn't, even though it is an Ethernet network, it's not involved with your network in the building because it's on our own network. It's a plug-and-play device, so it kind of auto-configures itself. That's what's really nice about it. Actually, you don't really have to know anything to use this. It's built and designed to have a lot of applications, so we develop applications for it. It's not just a one-dimensional product. We develop, improve, add applications over time. You can limit who can use those and who can see them. It has a way to back up all the transmitters that are connected to it in case something happens there. And the bottom line on it is so this can handle up to 20 EBTRON devices. So say 20 EBTRON Gold Series flow meters. All right, if on one of those flow meters, okay, all right, if we eliminate 30-foot extension cable on 2 4-probe measurement locations, so it's really two devices. So we have 2 EBTRONs that instead of you adding and making 40 or 50-foot cable on it, you said, no, I'll take it with a 10-foot of cable. I can get to the unit. I don't need to get to the unit because I have this smart display. Basically your cost savings paid for this device, and anything in addition to that, you've even saved more. Okay. And so we have, you can configure each one of the transmitters from a single location. You can see what everything is reading from this single location. It's got a really wonderful display app that'll toggle through all of the different connected devices and show you, what you're seeing here is a Gold Series with the humidity sensor app option. So, you've got airflow, you got temperature, you got RH, you got dew point, you got enthalpy. That's considered one unit, okay, one location. So you can have up to 20 of those connected to this device. It's got the equivalent of the EBLink reader. We've got a bunch of applications we're working on. The Field Match Wizard is the next to come out. It basically facilitates making one EBTRON match another EBTRON when they're in bad locations, like tracking on an air handler, okay? But we have a number of other applications in development. From a connection point of view, this version went with Ethernet, so basically, in this case, the red there is you're connecting to your building automation system with analog signals, and then you're connecting to the smart display through this Cat 5 cable, through an internet switch. That same model number basically can also have, we add the RS-45 card to it. Now you have RS-45 connection. And that once you've added the RS-45 card, you also still have the analog output. So it's, you're connecting to your building automation system like you always did. This is just connecting to the display using Cat 5. I told you we have the dual Ethernet card. It's designed for daisy chaining these back to the display just to facilitate wiring, eliminate the switch. Our products are all industrial IC, so there are basically industrial Ethernet switches on each one. You might have an Ethernet connection to your building automation system. We are not released this yet, but some folks have said, hey, you know what? We don't want to connect our RS-45 individual flow meters. We want to take it from one point, so you can take it from the display. for RS-45, and we did this. So we're doing the same thing with Ethernet. Okay. All right. So I think we're a little bit ahead of the game here. We definitely have the best technology. We have the most experience. We have 3-year warranty, advanced replacement. If you think something's wrong with the product, work with our service department. If it's something that we feel like is a warranty problem, we'll build you a whole new unit, send it out. Obviously, local reps that you have right now that are spending the time to get you together. And when you call EBTRON, you actually get real people. Okay? All right. Well, what a day. All right. Thank you very much. And I'll see you shortly.